Hi, students. The next topic to consider in chapter 20 of Cutnell and Johnson is on electrical power and energy. Okay, and so when we talk about a potential energy of, let's say, a power supply or a battery, we start off by discussing that it is given as potential energy is Q times the potential difference across, let's say, the battery. So there's going to be a potential energy given to these charge carriers, and we know by the work energy theorem, actually by the work energy theorem, we can also balance this out as work. We can also refer to this as work is Q times B by the work energy theorem. There's an amount of work being done to essentially push these charges into a current. Okay, so we want to we know that there is moving charge. We know that work is being done over a period of time. So the next idea would be, okay, we want to discuss the concept of power. Well, power would be what? Back in physics 1, we know that power, call it P, is the time rate of change of the work. I mean, in reality, it should actually be given as an instantaneous time rate of change. I should actually be using little d's here for derivatives. It should be, I really ought to be employing calculus here. All right, but so what I did to the left-hand side, I must do to the right-hand side. So if I apply a operator of, or a time rate of change operator on the left-hand side, I need to do the same on the right-hand side. So the time rate of change of Q times B. Well, the potential difference is, we're talking about at this point DC or direct current. So the potential difference, we haven't talked about. We're going to talk about alternating current in the next topic, but right now we're talking about DC. We're talking about if you have a battery or some way of applying a direct current, a constant current, you're also going to get a constant voltage. So you have a constant voltage, and so right now the voltage is a constant, so we can pull the voltage out. A constant does not get operated by the time rate of change operator, and so we can say that the power is then going to be B times delta Q with respect to T. All right, and delta Q with respect to T, we know what that is. That's the current. So the power delivered by a power supply or a power in a circuit is given as P equals BI. Given that I is the time rate of change of the charge. All right, so P equals VI, that's the power. That's the power in a circuit. It generally applies. I made no specific assumptions regarding this calculation. So it generally applies. Okay, so P equals BI. All I did is I said, well, I know the potential energy is taking a charge across a potential difference. I know by the work energy theorem that I can change it. I mean, I'm not worrying about signs right now. This actually would be negative. So this would actually be true as it stands. Work is Q times B, but I'm not worrying about the signs. And I can say, okay, then I know that the power is the time rate of change of the work, or the time rate of change of Q times V. And we expect V to be a constant, potential difference to be a constant. So we take the time rate of change of the charge, which is the current. So P equals V times I, very simple. Now, again, this generally applies, this equation. But what about, as I said earlier, we know that resistors get hot. So okay, P is V times I. Power in a circuit, or maybe power, we'll say power supplied by a voltage source. To a circuit. We'll just be more accurate here in our description. All right. Now, what about for a resistor? Let's just say we have a resistor. We have a simple case. Now, again, we're going to take a special case. We have a simple case of we have a battery, and a very simple case is just one resistor. All right. Here's my battery. Here's the plus. I'm sorry. Here's the minus side and the plus side, and this is the resistor. Now we know that resistors get hot. They experience what's called Joule heating or thermal heating. So resistors dissipate heat. They have what's called Joule heating. In fact, we have a face-to-face lab that we perform that actually measures this. Puts a resistor in a water and a calorimeter. As the resistor is giving off heat, it heats the water, and we can do calorimetry on the water to determine how much heat is being given off. And we essentially want to show that heat given off is actually given by the Joule heating equation, which I'm about to derive. And does that balance with the heat that one measures in the calorimetry experiment? And that we're missing that experiment. But so what happens here if I'm talking about power dissipated by a resistor? Again, this is specific to a resistor. Well, I know this formula in general. But I also know for a resistor, I know V equals IR. I know Ohm's law. That's an additional equation that I know for a resistor. Again, I'm specifically talking about resistors now. This P equals VI is generally true for a circuit, or basically the power delivered by a voltage source. Now we're talking about what is the power? What is the power that is dissipated by a resistor? So I can combine these two in a couple different ways. I can either eliminate V, substitute for V, and I can write that P equals I squared R. Sometimes you refer to Joule heating as I squared R heating. All I did is I just substituted for V from Ohm's law, or I can substitute for I from Ohm's law. I can also equivalently write that P equals V squared over R. These are two equivalent statements for the heat dissipated by a resistor. Again, it's a power dissipated by the resistor in the form of heat. Again, these are power equations. Their units are watts, a joule per second. And units on this one here is also watts. How many watts are dissipated? This is an equation that talks about how much heat is given off per unit time at a resistor. So everything below the squiggly line deals with resistors. These two equations deal with power dissipated by a resistor. You have to have a resistor or resistance in your circuit and have these two equations apply. This P equals VI generally applies. All I use P equals VI and I combined it with Ohm's law, given that, of course, the resistor is ohmic. All right, that's really all there is to say about power dissipated by a resistor. Let me work a couple of problems out. All right, I'm gonna erase this. All right, I'm gonna look at OpenStax 20.40. That says, what is the power of a 1.00 times 10 to the second megawatt lightning bolt? That's a lot of power. Having a current of 2.00 times 10 to the fourth amperes. All right, so this is a basic application of this equation. So again, we have a very powerful lightning bolt. It has, oops, I am mistaken. It's megavolt, I apologize. What is the power of a 1.00 megavolt or 100 megavolt lightning bolt having a current of 2.00 times 10 to the fourth amperes? What is that power? So you just directly apply the P equals IV equation, right? And again, you just plug in the values here. So you have this crazy large I, 2.00 times 10 to the fourth amperes, multiplied by 1 point. Now, again, this is megavolt, mega meaning 10 to the 6. So 10 to the 6 and 10 to the second, I really have a 10 to the 8. Be very careful with our units. Mega means 10 to the 6 already. Then I have 100 of that, so that's 10 to the 8. So the power, you multiply these two big numbers together, the power is 2.00 times 10 to the 12th watts. 10 to the 12th, that's a trillion. So 2 trillion watts from this lightning bolt. And these are not exaggerated values either. Good sized Texas storm, you're liable to see lightning bolts like this. All right, so that's the basic application of the power equation. Let's look at 20.43. OpenStax 20.43. That says how many watts? Does a flashlight that has 6.00 times 10 to the second coulombs pass through it in 0.500 hours. Use if its voltage is 3.00 volts. All right. How many watts does a flashlight that has, how many watts is a flashlight that has a 6.00 times 10 to the second coulomb pass through it in 0.500 hours use if its voltage is 3.00 volts? Probably not the craziest grammar here. But anyway, we have basically 600 coulombs pass through this flashlight in half an hour, and the flashlight has a potential difference across it of 3 volts, 3.00 volts. We want to find out the power. So we go to the power equation, right? I times V. Let's just kind of plan this out. We already have V. You have to find I, but hey, we have so many coulombs per time, so we can find I. So there's a little bit of work that needs to be done to find I. All right. So remember these numbers. I need some real estate. So kind of always make a game plan of how you're going to solve a problem. All right. So we want to use P equals IV or VI, I guess. I'll write these. So we know the volt. We know the potential difference is 3 volts. Now I is the time rate of change of the charge, or it's 6.00 times 10 to the second coulombs divided by 0.500 hours. Now, hours is not a base SI unit. I need seconds. So I need to make a conversion before I do anything else. So I know that an hour, hours cancel out, has 3,600 seconds. Now I can perform this multiplication and division and see that what I really have is 0.333 amperes. Great. Now I have VI, I can actually now apply the power equation. Power equals VI, or 3.00 volts times 0.333 amperes. I get the power is 1.00 watts. That's the power. Had to do a little bit of work to get the current. All right. Do another problem. I want to do OpenStack's 20.60. Let's see, that says A. What energy is dissipated? By a lightning bolt. Having a 20,000 ampere current. A voltage of 1.00 times 10 to the second megavolts. Seen these numbers before. And a length of 1.00 milliseconds. Okay. And then B, and harken back to physics 1. What mass of tree sap? Would be raised, or could be raised from 18.0 degrees Celsius to a boiling point, to its boiling point. And then evaporated by this energy. Assuming sap has the same thermal characteristics as water. Okay, so 20.6, the open stack says, what energy is dissipated by a lightning bolt having a 20,000 ampere current and a voltage of 1.00 times 10 to the second megavolts and a length of 1.00 milliseconds. Again, we've seen these numbers before. Those lightning bolts can take about a thousandth of a second. B, what mass of tree sap could be raised from 18.0 degrees Celsius to its boiling point and then evaporated by this energy, assuming sap has the same thermal characteristics as water. Now, when you see the results of this calculation, you're going to understand why you don't stand under a tree in a lightning storm or electrical storm, because sap literally will be exploding off of the tree. I'll tell a little story after this when I after this problem. So let's remind ourselves. Let's I need to realize it, obviously. So remember these numbers, and then let's work this out. Then we'll reach back to thermal physics to work out part B. So part A. Well, what do we know? We know that the power, again, is going to be the time rate of change of the work. All right, and of course we know the work. So the work is that energy that we're trying to calculate, right? So that work is going to be P delta T. Okay, so the work is the energy that we're trying to. We want the work out of this, so we're going to have a power over a certain unit of time. I'm going directly off of the definition of what power is to get the energy out of it. That's what I really want. Power over a period of time. Well, I know what power is. It's IV. In general, we just said that. So I could combine everything together and say, okay, well, combining this together, then we have the work done by this lightning bolt will be IV delta T. And I can apply that directly now. That's going to be the current, 20,000 amperes. The voltage, 1.00 times 10 to the 8th. It's like last time, it's 100 megavolts. Volts. The time, 1.00 times 10 to the negative 3 seconds. All right, I apply all these numbers together, I'll get an energy out of that, very large energy. Delta W will be 2.00 times 10 to the 9th joules, 2 billion joules. All right, so again, all I did is I applied P is the time rate of change of the work. I solve for the work. I know what the form of the power is for a current and a voltage. So essentially that's what the lightning bolt is. So I substitute that in for P, and I just multiplied it out. I know the current of the lightning bolt. I know its potential difference between the cloud and the ground. And I know how long the lightning bolt's going to take. It's very fast, 1 millisecond. Put all that together, in 1 millisecond, 2 billion joules of energy is being delivered. Now the question is, now we have a thermodynamics problem at hand. Now that we know we have 2 billion joules, okay, that's the answer to part A, by the way. Now we want to take that energy and find out how much tree sap, assuming the same thermal properties of water, how much tree sap can I not only take to the boiling point, but also flat out evaporate as well. Literally vaporize it. So let's see. Let's remember this number, 2 billion joules. All right, we're going to do part B now. We're going to parking lot this answer from the last problem. Then we're going to say, okay, well, we know the specific heat of water. So the equation we want to use now is say, okay, now we want to say, okay, this amount of energy is going to not only raise the temperature of a certain mass of tree sap, we'll say a mass M of tree sap, so MC delta T, but also it's going to evaporate it. Remember this? So MC delta T is the heat transfer that, again, heat is energy transfer due to a temperature change. Remember that. So again, if an object stays within phase, i.e. the tree sap is actually that's, yeah, the tree sap is actually being is being brought to 100 degrees. It's in phase, so as long as it stays in phase, it will be governed by this equation. Then we want to evaporate it. That's given by that equation right there. All right. So again, we're assuming the sap is like water. Again, we're not talking about a tree bark. We're talking about the tree sap. The tree sap is a liquid, so it stays within the liquid phase. And then so again, we're boiling. We're taking the tree sap. It's a liquid. To 100 degrees Celsius and evaporate. So the tree sap is below the tree bark. Okay, so when it evaporates, guess what happens to the tree bark? It becomes like a bomb, blows up. Right. So anyway, we're going to find out how much mass. The mass M is the mass of that tree sap. Now we're assuming the same thermal properties of water. So again, the specific heat of water, you look it up, it's 4186 joules per kilograms of degrees Celsius. And that is the specific heat of water, because we're assuming the same properties of water. Okay, so what we want to do is solve for M. So what's nice is we can actually pull M out. So I'm going to flip the equation here. So I'm going to extract M out of the equation. I'm left with C delta T plus L sub V. We have to look up by the way, we need to look up L sub V as well. L sub V for water, if you recall, is going to be 2256. It's a huge number, times 10 to the third joules per kilogram. So then that is, and remember from physics 1, evaporation and melting are two very expensive. So anytime you cross a phase bond, whether it's going from solid to liquid or from liquid to gas, that's an extremely expensive process, particularly going from liquid to gas. That is a huge number. So that's when you see the power from thunderstorms. A lot of that's because of this very large value for this is called the heat of vaporization. This is a very, very large value. So vaporizing is extremely expensive energetically. All right. And of course, the right-hand side of this equation is delta W. So simply solving this, I get M is going to be delta W divided by C delta T plus L sub V. All right, so let's do it. Mass, if I have enough room here, is going to be the delta W is this crazy number, 2 billion joules, 2.00 times 10 to the 9th joules, all divided by C is 4186 joules per kilogram degrees Celsius. Okay, delta T, well, delta T is what? It's 100 degrees Celsius minus 18 degrees Celsius. Then I have this L sub V, 2256. I'm going to erase some of these words here. 2256 times 10 to the 3rd joules per kilogram. All right, so plug all the numbers in. I will find out a crazy value for the mass. This is the mass of the tree sap. If you do all this, you'll find out that the mass is 769 kilograms. All of that is tree sap that can not only be raised to 100 degrees Celsius, but evaporated. And all of this would occur in a millisecond. So that tree effectively becomes a bomb. And it just blows off. I mean, and it's very funny how when it's none of this is funny, of course, but I had a young lady in my physics class who actually witnessed something like this. And there's a tree that was literally stripped of its bark. It was hit by lightning. And the funny thing is, it was about a day or so later. Well, actually, it was a day or so earlier to that storm, and I actually gave this lecture. And so she explained to her neighbors what had happened. That this tree sap is like water. It was raised to, not only raised from 18 degrees to 100 degrees, but it was actually boiled off. And she explained, that we're talking about a couple billion joules of energy was given from the lightning bolt to that tree sap. So all of this was kind of like she saw this problem, and then there was more or less kind of a direct lab for her. But this big storm that came by. So she, it's funny, funny how things work out sometimes. I gave this lecture, and then she witnessed this a few days later. She came back and told the class that. So that's really interesting. So so again, that's the reason why you don't want to stand under a tree in an electrical storm, because if the tree gets struck by lightning, it becomes basically a bomb. All that tree bark so the tree sap is below the tree bark. The tree sap within a millisecond will be taken. 769 kilograms possible of that tree sap can be automatically within a millisecond boiled and evaporated. That is a lot of power, a lot of energy dissipated in a very short amount of time. So again, this is a direct example of that, the power of a lightning strike. All right. Okay, so we're going to change topics now. That's the power from electrical current and voltage. So now we want to talk about how we experience electricity. So the next topic is going to be called alternating current. Versus direct current. Okay, so everything we talked about so far, it has been direct current. So essentially, most of the examples we've dealt with so far have used what's called direct current. We call that DC. So when I say DC, I mean, what are examples of this? So for instance, batteries. So DC, so a DC system utilizes what's considered a constant voltage source. Like a battery. I mean, you can have you can have a DC setting on your on the power supply, let's say in your lab. And however, we're going to find out though, however, in life, most electrical systems use alternating current. We call AC, where the voltage varies in time. Usually sinusoidally. I mean like a sine function. All right, so alternating current we call AC, direct current we call DC. Okay, so everything we've seen so far is DC, direct current. So what essentially does this look like graphically? All right, so it's kind of like, let's look at DC first and we'll compare AC. All right, so we have a voltage source, let's say a battery, and well, in time, let's say for instance, we're going to talk about direct current DC. So in time, like let's say a battery, it has a battery connected, and here's time axis, we'll say this is the voltage, and in time it's literally going to get turned on, and it's just going to have a constant voltage source of constant voltage. There's your voltage DC. Over time, it's nothing but a constant. All right, that's your DC voltage. And of course, we know if I have, let's say, just a simple resistive circuit, let's say this is my battery, and I have one resistor on it. My little simple example. Well, if that's V sub DC, then I know Ohm's law applies, right? If I know that the voltage drop across the resistor is going to be IR, and so I know that I could write down that the voltage across the resistor, V sub DC, is going to be IR. So we'll say I sub DC, specifying that it's direct current. I sub DC is simply going to be V sub DC over R. I mean, it's literally the same as V sub DC, except it's divided by a constant multiplier. So I could have, let's say, and it would also, if V sub DC is constant, then so is I sub DC. So the current is also going to be a constant. All right, so that's what we've been studying so far. We've been studying that we have a constant voltage, and again, it's the voltage source that essentially controls this behavior, the voltage source. So if I'm applying a voltage source that is DC, like a battery, then the current, then the system, the electrical system is going to behave that way. So again, if you're applying a constant voltage, you're going to get a constant current. Well, what do we get for AC now? So again, DC, pretty simple. Well, let's say, for instance, now I look at alternating current. What does that look like? Well, and then this is how most systems of the world work. And so alternating current essentially means that, and then again, this is controlled by the power by the power plant. The power plant is going to be is the source, the ultimate source of your power. It is doing things that with where the voltage varies in time, like a sine wave usually. And so again, there's nothing we can do about that. We have power lines that bring power to your house or your business. Those power lines they get transformed down. We'll talk about transformers, and the power the voltage that comes out of your wall varies as a sine function, and that's because that's how the power is being delivered to you. And I'm going to explain a little bit later that that's actually a better way of doing it. Even though at first you might wonder why would we do anything like that? So the voltage will vary sinusoidally. So let me make my graph look a little differently. So it could look like something like this. Here's my time axis. All right, and so this is voltage. We call the peak voltage, we call it V naught. That's your peak voltage. So again, the sine function is going to, it's going to take you from a max through zero to the same min, back to zero to the max, back to zero, same min, so on and so forth, on and on and on. Now, of course, all throughout, Ohm's law must apply. Let's say if this is indeed, this is now an AC, Ohm's law has to apply. So again, you're still going to get, in through your resistor, you're still going to get this relationship to be true. And so we know that anytime you have AC current is going to be whatever the DC current is, again divided by the resistance. So if I have a simple resistive circuit just like this, I know that I'm still going to have Ohm's law apply. It's just that it's not going to be a constant. It's just going to take on whatever the value is for the voltage and divide that value by R, the resistors. And so the current is going to be in phase. It's going to have its maximum when the voltage has its maximum. It's going to be zero when the voltage is zero. It's going to have its minimum when the voltage has its minimum. So it's going to be a sine wave that's going to mirror the sine wave that describes V naught, but it's going to have different amplitude. So it might look like something like this. So on and so forth. So again, this might be my I naught, my peak current. So again, you'll see that the current, and so for a resistive circuit, when I say a resistive circuit, I mean a circuit that only contains resistors. So for a resistive circuit, again, you could have a capacitive circuit as well, or we'll later understand here when we talk about magnetism, we can have an inductive circuit. But for right now, for a simple resistive circuit, the current and voltage are in phase. Again, I naught is your peak current. You might say, well, so what they're in phase? Of course they're in phase. Well, not so what, because we'll find out if we're to put a capacitor right here, that they would not be in phase. And again, later on, if we put an inductor right here, they will also not be in phase. They'll be 90 degrees out of phase in each case. And so we'll talk more about that when the time comes. That's a chapter 23 topic. We're currently in chapter 20. All right. And so we're going to briefly talk about AC circuits right now in chapter 20, kind of give you a little bit of a brief introduction to it, but we're going to concentrate on AC circuits in chapter 23. In fact, that'll be the only topic in chapter 23. All right. Right now we're in chapter 20. So right now, just suffice it to say that I and V are totally in phase. The peak value of the maximum of I occurs at the same time as the maximum of V. I takes on values of 0 at the same time V takes on values of 0. The minimum value of I occurs at the minimum value of V. So they literally oscillate, or they alternate in phase. All right, so that's important. Not necessarily so much now, but definitely when we talk about alternating currents as a total topic in chapter 23. All right, so what would this look like mathematically? And we're just going to talk about resistive circuits in this particular section. So mathematically, what would I have? Well, I would have V is V naught sine of 2 pi f t. F is the frequency. F is the frequency. Yeah, we talked about waves in the past, right? This is not a wave per se, but this is a time varying or sinusoidally varying function. It's a frequency, in hertz. And hertz again is the SI unit for inverse second. Okay, we call that the hertz to honor the great German physicist Heinrich Hertz. T, of course, is the time. Then, of course, since I is V over R for a resistive circuit, and we could write this as V over R, and I'm going from the equation right here. So V over R equals V naught over R sine of 2 pi ft. And of course, I could write this as I equals I naught sine of 2 pi ft. So again, this is generally the form of the time varying alternating current voltage. This is the form of the time varying alternating current, or AC voltage, AC current. All right, so they're literally in phase with each other. The frequency, oftentimes in our applications of electricity that you get in your house or business, the frequency is typically 120 times per second. The frequency is typically, we call this, well, frequency essentially the brightness. I mean, you take a fluorescent light bulb, a light bulb brightens and dims (120 times per second). Way too fast for our eyes to see. Now, there's certain things you can do, like for instance, if you look at a computer monitor and let's say click your teeth together, you can actually get a stroboscopic effect. You can actually get it so that you're actually missing some of these flickers, and then you kind of see that there is actually a flicker going on here. Anything that operates on AC power, like your computer, for instance, is going to flicker like this 120 times per second. All right. Now, the question that we then have is, okay, well, we talk about the voltage varying and the current varies. And the voltage varies because that's governed by the power plant. You know, the power plant is delivering electricity to you in this manner. So the voltage varies and the current varies. And what about the power? What would the power be? Well, the power, as you can imagine, is still I times V. All right, and so the power would then be I naught sine of 2 pi ft times V naught sine of 2 pi ft. So the power that would then be some constant, I naught V naught. They come out front, and then sine times sine, the same sine functions will be sine squared of 2 pi ft. So the power, interestingly enough, is always a positive value. It's a sine squared. Squares are always positive. So even when the sine function goes negative, it's still, the sine squared is still positive. So the power function looks something like this. Over time, here is the power. So on and so forth, right? And so the power function, so essentially, when you go and plug, or you go and say, I want to know what the voltage or the current is right now, the thing about it is you don't know what it is. It's anything from 0 to its plus peak to its minus peak. There's a range. And so for the same thing with the current, you don't know what the current is right now. You just know the range of the current. It goes from negative I naught to I naught. The voltage goes from negative V naught to V naught. So negative peak to positive peak. The power, again, by the same token, you don't really know what the power is at any given time. So what we do is we describe the AC sources, we describe their parameters by essentially statistical values. And so the first thing we would say is, well, I don't know what the power is, but I'm going to give you a statistical value. I want to talk about the average power. It turns out you can calculate this about 3 different types of ways. I'm going to do a geometrical argument for college physics. But imagine if I take P average, I'll call this P average. I'm going to assert that P average is 1/2 I naught V naught. Again, the peak on this power curve is going to be I naught V naught. That's your peak power. That's as large as this function is. Whether this sine function is, the sine is going to go from negative 1 to positive 1. So if the sine evaluates at 1, 1 squared is 1. So the peak power will be I naught V naught. Or negative 1 quantity squared is 1. Or again, the peak power is I naught V naught. So I naught times V naught is your peak power. I assert, through kind of a geometrical argument, that half of that peak is your average. So let's kind of try to draw this. Halfway up is the average. The way to look at this, and my drawing may not be too beautiful here, but half the time, or half the curve, half the total curve is above this dash line, and half the curve is below the dash line. This overall works out to be the average power. you can do this. I'm not going to do it here, but you can also calculate this using trigonometry, using trigonometric relations. Or integral calculus. Either way, you're going to get the same answers. This is not just something I just cooked up. I mean, again, this answer has been arrived at multiple ways. P average is truly 1/2 I naught V naught. You can get it from a geometrical argument, like I tried to do. You can also get it from just combining trigonometric relations. You can also do a simple application of integral calculus. Either way, the average power delivered by an AC circuit is going to be 1/2 I naught V naught. Again, that's what you want to work with, is the average power. So if I tell you I have a 60 watt light bulb, well, I'm telling you that the average power is 60 watts. I'm not telling you the peak power. When you say that something operates at a certain power, you're being told that that is the average power. So again, let me write that down. So when an appliance is said to operate at a certain power, this is the average power. Half the time, the power is greater. Half the time, the power is less. All right. So again, that's what you're being quoted. So 60 watt light bulb, that's your average power. It's not the peak power. That's the average power. All right. Now you can get the peak power, but it's multiplying by 2. Right. So now, in the same token, as I said, we don't know what the current or the voltage is at any given time. What we actually do is we describe it statistically by what's called the root mean square value. So we actually describe, again, we saw this nomenclature back when we talked about kinetic theory and gases. We describe AC systems statistically by an RMS current and an RMS voltage, referred to as IRMS, VRMS. Now, RMS means root mean square. Again, we talked about this in thermal physics studies. We talked about this in how you describe the RMS speed of a gas molecule. All right. What so if how do you calculate this? Well, if I want to find the RMS, I mean, I would basically add or take the mean of a set of data of the squares of a set of data. All right, so the mean's the average, and then I would take the square root to get it back to where it was, to get it back to the same unit. Take the square roots of this number. Now again, current and voltage in this particular case is continuous. Let me give you an example of, let's say, a discrete system, for instance. Let's just say, for instance, I have data. And I don't know what I'm measuring, but I'm going to measure data as, let's say, x1, x2. I will say I'm measuring something. I'll call it A1, A2, A3, and A4. And I want to find the ARMS. So I want to find ARMS. I have 4 data points. Just make things simple. I'm going to find what I call ARMS. Well, again, what do? Root means square. I add up all the squares. So I take A1 squared plus A2 squared plus A3 squared plus A4 squared. I'm adding up all the squares, getting a sum of all those squares. How do I find the mean of those squares? Well, I divide by the number of these data elements. So in this particular case, I would divide by 4. All right, so I've added up all the squares. I am now taking the mean. And then what do? Well, then I take the square roots, because right now I have everything in terms of A squared. So this could be currents. I'd have Coulomb squared, ampere squared, ampere squared, ampere squared, ampere squared. So I'm going to have the average of a bunch of ampere squareds, a bunch of current squareds. What I want to get is the current. So again, this A can stand for voltage, current, whatever. I'm just being very general. So to get it back to the same units, I take the square root of the whole thing. And that gives me ARMS. That gives me whatever these generalized quantities are. That tells me the RMS. It's the root mean square. Root mean square. These are all squares. All right. That's what we do with, now again, this is a specific example of a discrete set of data. What we have is continuous current and voltage. We would actually have to do this calculation through integral calculus. However, we don't need to, because we have a nice simple result that is given to us via integral calculus, and that is simply the following. We literally know, and this has been done for us, we literally know that IRMS is literally nothing more than, again, you'd have to do integral calculus to figure this out, but we're just going to take this as a result. It is the peak current divided by the square root of 2. Likewise, VRMS will be the peak voltage divided by the square root of 2. So that's what you get. So when you say that, we have, let's say, our household appliances in the United States, our household appliances are given in terms of we're told we have 120 volt appliances. So you have 120 volt AC that comes out of your wall. All right. What they're telling you is that's the RMS voltage. Anytime you get quoted any numbers, when you talk about AC system, you're given the RMS numbers. So in the United States, household wiring, so household wiring, you plug in something in a outlet, is at 120 volts AC, as it's always said, 120 volts AC. This means, I mean, in many parts of the world, their houses and businesses are wired for 240 volts AC. United States is wired to about half of what much of the world is wired at. So when you go to use your appliances, so let's say your razor, your electrical razor, or your hair dryer, whatever it is you want to say, you're going someplace in Europe or some other place that's not the United States, then you're going to have to adjust, and that's what's called an adapter, in order to make sure you don't destroy your appliances if you want to use them in France, for instance. All right. So what we're actually told here is that when you talk about 120 volts AC, you know, for instance, we'll just kind of talk about the United States. What we're being told is that VRMS is 120 volts. All right. So half the time, the voltage is actually higher than this, and half the time it's lower than this. And so what would the peak be? Well, let's see. If I want to find the peak, I know that VRMS is the peak voltage over the square root of 2. So I could find the peak voltage by just taking the square root of 2 and multiplying 120 volts. So the peak voltage, I didn't do this calculation. Let me do it real quick for you. So the peak voltage is the square root of 2 times this. So 120, the square root of 2 times 120. 170, 169.7. So in the United States, the peak voltage can be as high as 169.7 volts. But on average, and again, you know, it's going to go higher than that, and it's going to go, you know, so the peak voltage will be 169.7 volts roughly. So that's what we know when we talk about 120 volts AC in the United States. It could be higher. All right. And so now the interesting thing is, when we do circuitry, we can actually use the same equations we had before. So in analysis of AC systems, we can use all of the equations from DC, provided that we employ VRMS for all the voltages, IRMS for all the currents, and average power for all the powers. So anytime you see, you know, essentially any of the kind of problems that we did before, if we're talking about an AC circuit, we're talking about AC system, a time varying AC system, then we can perfectly free to use all the equations we did before, as long as we use these values. So for instance, I can use Ohm's law. I can write that VRMS is IRMS times R. I'm perfectly free to write that. I can write also that now again, if I take a look at this, the average power, does this work out? Well, the average power, well, it should be IRMS times VRMS. Yeah, I know the power is V times I, right? Well, does that work out to be the average? Does that work out to be the average power? Let's see. So I know that IRMS is I peak divided by the square root of 2. And I know the VRMS is V peak, the peak voltage divided by the square root of 2. And that becomes I naught V naught divided by 2. Exactly what I told you the average power was. So again, I can use all the equations from before. I can instead of P equals IV, I can use IRMS times VRMS. And that, yeah, indeed, that does work out to be the average power. Likewise, I can use the other equations that I learned. You know, the power dissipated in a resistor. Remember, for the resistor, power dissipated in a resistor. I can use those equations too. So I can use I RMS squared times R. I can also say that the power dissipated is V RMS squared divided by R. Again, all the equations that I derived before for DC circuits, DC systems, I can use all those equations as long as I use IRMS, VRMS, and average power. I'm perfectly free to do that. Okay, so now here's the $1,000,000 question. Why do we want to even do this? It seems like a very weird way to deliver electricity. Right? So literally you're saying, so kind of talk about the why. Okay, and this kind of goes into some interesting stories. So why use AC power? Why use an AC power distribution? Why are we even doing this? I mean, again, you think about this for a moment, most power distributions are AC. And so we're going to find out that, most power distributions maybe not, if not all, in the world are AC. One of the big challenges you need to have, again, we in the world, you always want to do things, with economic sense. So economies of scale demand that we use large power distribution systems, or large power plants, we'll say, to deliver power to many people, many households and businesses rather than have many small power plants. So again, the problem we have is the concept of having to deliver this power. We have to deliver that. We can generate this power, but the question is, how do we get it to you? How do we go from, we deliver some power, we have a power plant, let's say, at, a nearby river, or, nuclear power plant, or however it is that we get our power. how do we get it from that power plant to your house? And we don't want to be having power plants everywhere. We don't want to have a power plant in every 10 streets or something like that. That doesn't make any sense. So we need to have one large power plant and deliver power. So we have delivered over these power lines. And so that's the big question too. Is, well, we know that even we have a good conductor, we know we're going to have energy losses. So yeah, you deliver power with power lines, but you're going to have energy losses. You have to deal with that. And so we have to try to figure out, okay, how do we do this? And be able to do it in an economic sense where we're not, first of all, it's not going to cost an arm and a leg for power. You wouldn't want to be, I mean, it's bad enough, the kind of power bills you pay in Texas in the summertime. You wouldn't want to be paying 3 times or 4 times that amount regularly. You want it, so you, the consumer, do not want to be, paying for power with an arm and a leg, and at the same time, the engineer or the scientist who's developing these power plants doesn't want to develop something that's going to do nothing but just lose energy. So we have to come up with a way of delivering power. We know we need to do that. We need to deliver power in an economic and feasible manner. And so that's the challenge that we have. We need to deliver power. We deliver power over long distances and minimize power loss. So I'm going to do an example out of OpenStax that's going to kind of drive the rationale for using a power distribution system. Okay, so let me look at OpenStax example 20.10. And then what I'll tell you afterwards will make a lot more sense. All right, so example 20.10 says, A, what current is needed to transmit 100 megawatts of power at 200 kilovolts? All right, and then B, what is the power dissipated by the transmission line? If they have a resistance of 1.00 ohm. Then C, what percentage of power is lost in the transmission line? Very important engineering calculation. Okay, so What current is needed to transmit 100 megawatts of power at 200 kilovolts? B, what is the power dissipated by the transmission lines if they have a resistance of 1.00 ohms? What percentage of power is lost in the transmission line? Again, if you're an engineer, developer, electrical engineer developing power lines, this is a very important question for you, is I'm going to lose something, but how much? What's an acceptable loss? All right, so remember these numbers. So again, the thing to keep in mind here is that we are transmitting a lot of power at a very high voltage, 200 kilovolts. Okay, so again, a lot of power at a very high voltage. All right, and then I'm going to kind of compare and contrast. So remember this. All right, so here we go. Let's work the problem out. All right, so again, real life situation here. So we're told that our average power is 100 times 10 to the 6 watts. Okay, told that. We're also told that VRMS. Again, we're talking about AC systems, talking about real life. VRMS is 200 times 10 to the 3rd volts. And we also know the resistance of the power lines, one big long resistor. It's 1.00 ohms. All right, this is what we know. Now, we want to figure out what is the average power. Well, the average power, again, we know we can just use the equations that we had before. So it'll be IRMS, VRMS. All right. And so we're asking what the current is. Part A wants to know the current. All right. So I know the average power. I know the VRMS. I can use all the equations that I derived before for DC systems. I can use those for AC, provided, of course, that I am using the RMS values, right? So IRMS will be P average divided by VRMS. And we work this out, you have 100 times 10 to the 6 watts divided by 200 times 10 to the 3rd volts. And you find out that IRMS will be 500 amps, 500 amperes. Again, with this particular potential difference or voltage, this particular power delivery, this is the current that goes along with that in accordance with P averages, IRMS, VRMS, right? Now the question is, part B says, well, what is going to be your power loss in the transmission lines? How do you do that? Well, again, as we said, the power loss in the transmission lines will be IRMS squared R. I squared R, right? And so if I do that, I find out that the power loss will be 500 amperes squared times 1 ohm. The power loss, again, this is the power loss due to heat through the transmission lines, 2.50 times 10 to the 5th watts. Well, that may seem like a lot of power to lose, but the question is, what's the percentage loss? And well, that's part C. The percent loss, we're going to look at part C now. Well, that's going to be the power loss divided by the total power. the average power, times 100%. All right, so I'm running out of space here, but I want to try to put the calculation in one sitting here. So that's going to be the percent loss will be this 2.5 10 to the fifth watts divided by the 100. Let's see, I'm running out of space here. Let's stick it down here. It's a very important calculation. I like to stick it all in one sitting to compare and contrast here. But all right, so let's stick it over here. So percent loss will be 2.50 times 10 to the fifth watts divided by 1.00 times 10 to the eighth watts times 100%. I find out if I do that, my percent loss. All right, my percent loss is only going to be 0.250%. Now, that is totally acceptable. So again, I got the average power by IRMS times VRMS. I mean, I figured out IRMS, okay, and that's what I did. I was given VRMS and the average power. I determined IRMS. Then I figured out how much loss, how much power loss will be because of the current going through these transmission lines have resistance 1 ohm. So that's I squared R. IRMS squared times R. The power loss will be 2.50 times 10 to the fifth watts. The percent loss is the 2.50 times 10 to the fifth loss, the power loss divided by the total power, 1 times 10 to the 8. Multiplied by 100%, you get 0.250%. That is a totally acceptable loss percentage. That is absolutely, 1/4% is totally acceptable loss. Now, if we make a comparison, let's say, for instance, that we decide, well, let's instead we want to employ the same average power, but I don't like these high voltages. All right, so instead I'm going to be like Thomas Edison. I'm going to say, no, that's crazy. I want to do, let's say, 25 kilovolts instead. All right, so instead of this, I want to make this 25. Use the same equation. So if I do that, then I find out, and I do the same calculation, I'm going to find out that, again, I'm just kind of giving you a comparison here. If I say that's 25 kilovolts, I will find out that I have now 4,000 amperes for IRMS. All right. And if I plug that in, if I go and say, well, how much loss is that? Well, 4,000 amperes. Put that in there. I'm going to find out that power loss is going to be basically 4 squared 16,000. No, it's more than that. Sorry. 1.60 10 to the 1, 2, 3, 4, 5, 6, 7. 1.60 10 to the 7th watts. Sorry about that calculation earlier. Okay, that's what it becomes. Then I do my power loss. Well, now I have to put 1.60 times 10 to the 7th here. And I get a really ugly number of 16%. Totally unacceptable. That is the crux of the argument that occurred between Thomas Edison and Nikola, and then so Thomas Edison was on one side. Thomas Edison said, "No, this is crazy. Well, you can't be transforming high voltages like that. That is absolutely dangerous. The high voltages, that's a danger to society." On the other side of the argument was Nikola Tesla, and George Westinghouse, who said that you need to minimize these losses. You can't have 16% power loss. So if you go with lower voltage, to deliver the same power in the same transmission lines, you're literally gonna suffer a 16% power loss. We cannot live with 16%. With higher voltages, when this number becomes 200 kilovolts, this number then becomes 0.25%. That is an acceptable amount to live with. And so, well, here's the issue. So you had this big argument between Edison on one side, Westinghouse and Tesla on the other. All right. So again, as we saw, we have to, in order to be able to transfer power, we have to be able to, we must have high voltage power lines, very high voltage. Now, we're going to find out that that's okay because we actually have what is called a transformer. And well, we won't study transformers until a couple chapters from now, but we will learn about transformers that can step down the voltage, the high voltage, from the power lines to a reasonable or more reasonable 120 volts AC in your homes and businesses. Okay, so we will learn about what is called a transformer, which makes this all possible. And the other important thing about transformers, and again, this is all stuff that, I'm kind of teasing you a little bit, but we're going to learn this in the next couple chapters. One of Maxwell's equations is called Faraday's law of induction. So that's a chapter 22 topic. Due to Faraday's law, again, this is all blah, blah, blah for right now to you. That's okay. But due to Faraday's law, transformers must use AC circuitry or AC current. And I'm not going to explain why yet. The important thing is Faraday's law requires time, it requires current changing in time. I'll give you that as a spoiler. But change in time is absolutely necessary for Faraday's law. And so we can have high voltage power lines, as long as we can step it down with a transformer, we'll talk about transformers in chapter 22. And transformers are Faraday's law of induction, one of the four Maxwell's equations, one of the governing equations of the universe for electromagnetic theory, requires change in time. So you must have AC currents in order to even make this happen. So if you want to step down from a high voltage, you have to have a high voltage, as I said in the last calculation, in order to minimize your power losses. The transmission lines, you must put high voltage across those transmission lines in order to minimize the power losses to be at an acceptable rate. or sorry, at an acceptable level. And then in order to be able to bring a reasonable VRMS to your house or business, you must have a transformer. Again, we haven't talked about transformers yet, but a step down transformer will step it down from the 200 kilovolts down to the 120 volts that you need. And in order to use a transformer, Faraday's law is the Maxwell equation behind transformers, and it requires current changing in time, which means that you have to use AC current. So again, these are the various arguments used by Nikola Tesla and George Westinghouse. And so there's a big war essentially that kind of occurred between them, all right, over how do you do this. Thomas Edison thought it was insane to have high voltage power lines throughout a town. So Thomas Edison, you heard about him, the inventor of the light bulb. Thomas Edison actually thought that AC shocks were too hazardous. So in the 1800s, he wired New York City with DC. I mean, it didn't really work very well. On the other hand, George Westinghouse and the great Nikola Tesla successfully argued for AC, and they won. Now, if you want to study a guy who is tremendously interesting, and I think people are learning about him more and more, it's Nikola Tesla. Nikola Tesla is kind of one of the unsung people. He didn't really fight for himself so much. He was probably as brilliant as Albert Einstein, but he wasn't a real political person. He was actually a personal friend of Albert Einstein's. But he was somebody who was kind of you kind of say you make him a bizarre person, I suppose. He's like Newton. He never married, and he didn't like Newton. He didn't have any significant relationship with any woman. In fact, he was somebody who just absolutely involved himself or immersed himself in his physics work, and he made significant contributions. It was interesting. He was kind of a guy that kind of came with a kind of certain aura about him. Even when he was born. He was from Transylvania. He's from Romania, Transylvania area and stuff. And during his birth, it was during a massive thunderstorm, and the nurses, they were like, "Oh, that's a bad omen when you're born, when there's a massive, significant thunderstorm outside, right?" And so he was already born under some sort of an omen. And there's all kinds of crazy stories about Nikola Tesla, and contact with extraterrestrials and all kinds of crazy stuff, right? But when Tesla, here he is. He's a man that is responsible for powering all the houses and businesses of the world, right? I mean, the man should have been phenomenally wealthy. He died basically broke. He lived every day in a hotel room. I think it was a Waldorf Astoria hotel. Every day he would eat dinner at the exact same time, at the hotel. So I don't know what it was, 8:15 p.m., whatever. He ate the exact same thing every single day. The staff over there knew exactly who he was and what he wanted to eat, and so they already had it prepared. So and I guess as the story goes, when Tesla died, I guess the U.S. government came in and swooped into his hotel room and took all of his papers because they were thinking he was working on some really, really interesting phenomena. So Nikola Tesla, we honor him with the unit for the magnetic field. We'll talk about that later. The Tesla. Elon Musk is actually honor him quite a bit. He had the Tesla car. He's one of Elon Musk's heroes. And so Nikola Tesla is a person of, definitely worthy of reading about. He was very, very amazing scientist. And honestly, he is the reason why we have electrical power in our households and businesses. And anybody in the world can say that. He delivered electrical power to the entire world. All right. So what we're talking about here with AC systems, a lot of it is attributable to the great Nikola Tesla. All right. So I'm going to work out a problem here. 20.72. Opus X 20.72. Sets. A. What is the hot resistance? Of a 25-watt light bulb that runs on 120 volt AC. Okay, and then B, what is the bulb's operating temperature? I'm sorry, if the bulb's operating temperature is 2700 degrees Celsius, what is its resistance at 2600 degrees Celsius? I'm going to kind of reach back for previous stuff to be studied. Okay, so 20.72. What is the hot resistance of a 25-watt light bulb that runs at 120 volt AC? And B, if the bulb's operating temperature is 2700 degrees Celsius, what is its resistance at 2600 degrees Celsius? All right, so I'm going to do some erasing here. All right, 20.72A. So we have P average. Again, anytime you're given any kind of a power for something that operates on AC, which is pretty much like everything except for like batteries, you have 25 watts. So it's 25-watt light bulb, which means that's average power, is 25 watts. That's what that means. Again, the voltage coming out of your wall, VRMS is 120 volts. All right. Now, we want to find out what the resistance of this light bulb is. And so the hot resistance is called. So again, I would pick, one of the power equations. So given I know voltage and I know power, I would pick this one. P average is VRMS squared over R. Again, this is the dissipating power for a resistor. So any kind of electrical appliance that you plug in acts like a resistor. So if you plug in a toaster in your circuitry, that's a resistor. You plug in a light bulb or a lamp, that's a resistor. So to a circuit, you plug in an appliance, effectively you're putting on a resistor. Okay. So again, this is something that's going to dissipate power. It's going to heat up. We want to find the resistance. So again, I can solve for this. R, just changing partners here, B RMS squared over P average. And so that's going to be 120 volts, quantity squared, divided by 25 watts. So the resistance in this calculation would be 576 ohms. All right. And then part B says, okay, well, we'll say that this is occurring at 2700 degrees Celsius. What would its resistance be at 2600 degrees Celsius? All right. So how do we do that? Well, again, we harken back. This is A. I need more real estate here, so this is A. All right. So we'll say now that all the things I just got done computing, the temperature T naught is 2700 degrees Celsius. And I'm interested in what is the resistance. So we'll say that this is R naught. What I just got computing now is R naught, which is 576 volts. I'm sorry, ohms. That is the resistance given that the operating temperature is 2700 degrees Celsius. Well, I want to consider an operating temperature of 2600 degrees Celsius, and I want to find R. I want to find the corresponding resistance now. Okay, so we go back to that relationship that says, well, we know the resistance varies with temperature. All right, so we know that R is R naught times the quantity 1 plus alpha delta T. Well, I have to look up, well, first of all, delta T, be careful here. Delta T will be T minus T naught, or 2600 degrees Celsius minus 2700 degrees Celsius. My delta T is actually going to be negative 100 degrees Celsius. I mean, I am actually considering a lower temperature. All right, and I need to look up alpha. I'm assuming the filament is made out of tungsten. So alpha for tungsten, right? I have to look this up. 4.5 times 10 to the negative 3 per degree Celsius. Again, this is the coefficient of thermal resistivity, as it's called. Again, this is for tungsten. All right, assuming that the light bulb filament's made out of tungsten. So it's a matter of now just directly applying R. So R is going to be the 576 ohms times the quantity 1 plus, we have this 4.5 times 10 to the negative 3 multiplied by negative 100. Again, for space purposes, I'm leaving off the units there. So I find out when I do all this calculation that R at 2600 degrees Celsius will actually be 317 ohms. So for tungsten, the resistance is going to vary wildly over 100 degrees Celsius range. So again, the 576 ohms that I calculated earlier assumed that it's being calculated at a temperature T naught of 2700 degrees Celsius. I would like to operate maybe this particular light bulb at, let's say, 2600 degrees Celsius. And so again, I want to find out what is the resistance at 2600 degrees Celsius. I use the relationship R is R naught times 1 plus alpha delta T, where alpha is the temperature coefficient of resistivity given an inverse per degree Celsius. And I look it up for tungsten, assuming that the light bulb filament is made out of tungsten. And so I run through that equation, being careful that I'm looking at a delta T of negative 100. I'm looking at a temperature that's 100 degrees less than the operating temperature that I assumed earlier. And I'll find out that the resistance has reduced down to 317 ohms. All right. I'm going to look at OpenStack's 20.73. All right, that says certain heavy industrial equipment. Uses AC power. That has a peak voltage of 679 volts. What is the RMS voltage? All right, so again, certain heavy industrial equipment uses AC power that has a peak voltage of 679 volts. What is the RMS voltage? So again, what is the relationship? Well, we know that VRMS is V peak or V naught over the square root of 2. And we know that V naught is the peak voltage, that's 679 volts. So literally, this is nothing more than just kind of a direct application here. So VRMS is the 679 volts divided by the square root of 2. Or VRMS, you'll find out is 480 volts. For heavy industrial equipment. All right, 20.75. That says military aircraft use 400 hertz AC power. Because it is possible to design lighter weight equipment at this higher frequency. Okay. What is the time for one complete cycle of this power? Okay, so military aircraft use 400 hertz AC power because it is possible to design lighter equipment at this frequency. What is the time for one complete cycle of this power? So again, what are you given? You're given that the frequency is 400 hertz. Well, frequency is the number of cycles per second. So one cycle is the period, right? So you're being asked for the period. The period is just 1 divided by the frequency. All right, so that's 1 over 400 hertz. Or the period, capital T usually, again, is the letter for that, will be 2.5 times 10 to the negative 3 seconds, otherwise known as 2.5 milliseconds. And that is the period for one cycle, which is being asked. And all I took is a frequency, and of course, this is if you have a frequency, a period is 1 divided by the frequency, given that the frequency is in hertz. It's kind of a review of chapter 16, chapter 17 stuff, actually, from physics 1. All right. Look at 20.76 open statics. All right. That one says a North American tourist takes his 25-watt uh, 120-volt AC razor to Europe. Finds a special adapter and plugs it into a 240-volt AC. .40-volt AC. Assuming constant resistance. What power does the razor consume as it is ruined? All right. A North American tourist takes his 25-watt, 120 AC razor to Europe, finds a special adapter and plugs it into 240-volt AC. Assuming constant resistance, what power does the razor consume as it is ruined? All right. So again, this example of, you have an American product or North American product that's designed for one kind of a system. You're trying to plug it into another system that's rated in a different way. So let's see what we have here. So let's look at this. Find ourselves in these numbers. All right. So again, we want to look at P average is B RMS squared over R, and we want to find the resistance. So we're going to assume, okay, he's in the United States, or he's in North America, and so in this particular case, we want to find the resistance of this razor first of all, what it's designed for. So that would become V RMS squared over P average. And a razor is going to consume a certain amount of power, but in North America, VRMS is 120 volts AC. So that means that the resistance of this razor, I can rate it right now. I say I know what the power is, so it's going to consume basically 25 watts of power. That's what it's designed to do. So 120 volts squared divided by 25 watts. So the resistance for the razor will essentially be 576 ohms. But now I'm going to go to Europe. In Europe, VRMS is now going to be 240 volts AC. All right, so I'm going to misuse my thing. So what power is it going to consume? Again, it's the same razor. So the resistance that is computed in North America is going to be the same. I mean, I know the values in North America, and this is what the value. This is how the razor is designed. It's designed to be using a 120 volt AC outlet, and it's designed to consume 25 watts of power. Now I'm going to misuse it. I'm going to plug it into a place in Europe that uses 240 volts AC. What is the power that's going to be consumed by the razor now? Well, again, using the same equation, now the power in Europe is going to be this VRMS squared over the same R, because that's the design factor of the razor, no matter where I go. Well, that would be 240 volts, 20 squared, divided by the same 576 ohms. Now the average power, I'll call it, to denote it differently, I'll call it prime, average prime. I'll say then it's going to be 100 watts. That's what the razor is going to consume for a very brief amount of time in Europe before it gets burned up. Because it's not designed to run 100 watts, it's designed to only run 25 watts. Okay, I'm going to do another problem out of OpenStack. So I'm going to do 20.79. All right, OpenStacks, 20.79. What is the peak power consumption? Of a 120 volt AC microwave oven? That draws 10.0 amperes. Oops, 10 amperes. Apologies. 10.0. All right, so that says, what is the peak power consumption of a 120 volt AC microwave oven that draws 10 amperes? So again, anytime you see numbers being quoted regarding some appliance that you just normally use in your house, those are RMS values. So we're being given, I'm going to erase this so we're being given 120 volts RMS and IRMS of 10 amperes. Again, these are RMS values when we are talking about our regular usage of appliances. So VRMS is 120 volts. What the microwave is designed to run on households in the United States or North America. IRMS is given us 10 amperes. That's the current that is designed to use. That's the RMS current. We want the peak. Well, we know that the average power is essentially going to be IRMS, BRMS, right? We use the same formulas from DC, which is IRMS, BRMS. We use the same formulas for DC, but we make sure we use the RMS variables. So IRMS, 10 amperes. BRMS, 120 volts. The average power is what you're going to get when you do that. Again, the power that you use now for AC systems is the average power. So the average power is going to be 1200 watts or 1.20 kilowatts. Now, we want the peak power, right? So remember, the average power is the peak power divided by 2, right? And so we want the peak power, we would say the peak power is just twice the average. Or 2 times 1.20 kilowatts. The peak power will then be 2.40 kilowatts. That's how all these work together. When you talk about, 1.20 kilowatts, that's an average power. That's the power you get out of this. But again, it's going to be half the time it's going to be above that and half the time below it. The peak is 240. Or sorry, 2.40 kilowatts. All right. The next topic is one that really is something I try to give when we meet face to face, is that, there's inherent dangers in any physics lab. I mean, if you go to physics 1, yeah, you could drop something on your foot, or you could trip over something, or you could be doing the centripetal force lab and be spinning a ball around, hit somebody in the head or hit a computer monitor or something. There's ways of having accidents in any physics lab, but it just seems like when you're talking about electrical systems, your ways of having accidents is much more significant and possibly deadly. All right, and so I think what I want to talk about briefly are electrical hazards. So again, when you're talking about labs, this is an important topic that I try to have with my students, is to say, look, I don't want you horsing around in the lab at all, ever, any physics lab, whether it be physics 1 or physics 2. But honestly, if you're not paying attention to where your hands are in physics 2, it could possibly be a fatal experience. I mean, you don't want that. Absolutely. I mean, I have never had anybody get hurt in any lab that I've ever been overseeing, because I'm extremely cautious about making sure my students are safe. But again, I give this talk, and and when I give this talk, sometimes my students are a little sheepish afterwards, because they're really, really, really watching where their hands are after I get done talking about this, because this is something that you don't want to play with. Electricity. Electricity is one of those things that you want to be very, very careful and very respectful to it. So there's a couple different major hazards that one can have, electrical hazards. One is called a thermal hazard. And the other one is a shock hazard. All right, these are 2 types of ways. So thermal hazard basically is you have excessive electric power. So for whatever reason, excessive electrical power causes uncontrollable, or we'll say causes excessive thermal power which can cause a fire. And then the shock hazard is essentially electric current goes through a person. Okay, so we're going to talk about each of these in terms. But again, the major hazards when you're talking about, let's say, when you're dealing with electrical systems, is you have to be mindful of getting hurt. You have to be mindful of your safety. Okay, and I'll kind of talk about this. So first of these is really going to be more like thermal hazards. It's going to be more like, how do you design something in your house, or how you make sure that, you know, for instance, an excessive thermal hazard does not occur. All right, and so we'll talk about that. And then the ones that probably more directly applies to you as an individual would be the shock hazard. All right, so let's talk about, you know, kind of each of these in turn and how would these actually come about. So essentially, when you have a thermal hazard, I mean, what causes it usually? Well, electric power causes undesirable heating effects. Whenever electric energy is converted to thermal energy at a rate faster than it can be safely dissipated. So whenever electric energy is converted to thermal energy at a rate faster than it can be dissipated. You want to get rid of the thermal energy. You know, you'll hear on a hot day when you're driving your car, oftentimes you'll hear, you know, your car, a fan will turn on. Well, what's happening is there's some sort of a sensor that essentially recorded that there is approaching excessive amount of thermal energy in your motor in your car. The purpose of the fans being turned on is to blow it out, is to get that hot air out of there. You want to blow that air out. You'll notice that when you have a computer, you know, there are fans in your computer. The fans turn on, and the purpose of those fans is to blow the heat out of the computer. Again, you don't want to have excessive heat in any kind of an appliance. You want to try to get it out of there. You know, you want to dissipate it. If it doesn't dissipate naturally, you want to help dissipate it by blowing it out. All right, and so classic example of this problem is a short circuit. All right, and this is a low resistance path. Made available to a current. call that a short. So for instance, maybe you have wires. So for instance, maybe the insulative coating on two wires has worn through. Allowing them to touch. So hence, no resistance. They're going, touching, and so you may, so hang on, allowing them to touch. So you have insulated coating on wires that have worn through. You have wires that are touching that are not supposed to touch. So so for instance, what happens when that happens, what the problem that occurs is that you have an excessive current. So let me kind of explain this. So for a short circuit situation, such undesired contact, so it's such an undesirable contact in a short circuit essentially the power dissipated in a short would be P average is our VRMS squared, but over R, which is a very small resistance. Now, since R is very small, P average thermal energy is very large. The thermal power delivered is too large to allow enough time for dissipation, for power dissipation, for heat dissipation. And melting and possibly fire ignition can occur. You can ignite a fire. Essentially, you have the I squared, you have the V squared, VRMS squared over R is excessive. Again, this is a power, this is an energy delivery, this is an energy being delivered, heat energy being delivered over time. When that is excessive, there's not enough time for the heat to actually be dissipated. So there could be so much heat, you can actually cause melting and possibly the ignition of a fire. You get electrical fires happening this way because you have shorts that occur. Now you could also have a problem with overloading. So again, this is a short circuit issue. You also could have a problem with overloading a circuit. That could also be causing a thermal hazard. So another thermal hazard occurs. So you can get a thermal hazard by overloading the circuit. So as we know, another way of this of talking about thermal energy is I squared R. If I is too high, if the current is excessive, unfortunately, you square it. So you make it even worse. So the heat dissipation P becomes too large. And again, the same stuff happens before. You have melting or fire. Circuit breakers are designed to turn off a current, to shut off a current that exceeds a threshold, to prevent this. So a couple summers ago, my air conditioning system failed. Essentially, I knew about it because every single time I turn on the air conditioner, I would trip the circuit breaker. And so, I mean, it ended up being a bad capacitor, but essentially, you turn it on and the current would go, I believe it was 20 amperes. I forgot. It was trying to draw more current than that. And of course, you don't want to draw more current than that because of this very reason. You have excessive heating and possibly a fire or a melting or destruction of your device or your appliance. So again, this is the situation. This I squared R, excessive heating, the circuit breakers that are allowed that trip if the current is too excessive. That current, those circuit breakers are designed to prevent against this excessive thermal hazard with excessive I squared R heating. Again, direct applications of the stuff we just got done learning. And then we have the shock hazards. Okay, so thermal hazards are really about, protecting you, your appliances, from excessive I squared R or B squared over R heating. Now the shock hazard is different in that is if a human being accidentally gets in contact with let's say a hot wire. So shock hazard. All right, so basically, as you can imagine, it's electrical current inadvertently passing through people. All right, and so now we do use electrical current to block back pain. We also have, there's also, it's not always bad for electrical current people. There is electrotherapy. You can block back pain. In fact, there's research done to try to get the nerves going and in the limbs of paraplegics so they can walk again. So again, there are good applications for electrical current being put into people. However, again, when you accidentally touch a electrical circuitry, most of the time it's not going to be beneficial. It's going to be detrimental. So the major factors that determine shock, severity of shock. So the major factors that determine severity of shock. So what are they? Well, kind of straightforward, I think. The amount of the current. How much current is going through? It's really more the current than the voltage. You know, it seems like people have you know, they're worried about the difference of the voltage, right? But again, it's kind of like, you know, you might kind of wonder how in the world I'll see a high tension power line and I'll see birds walking around on those high tension power lines. And of course, you know, before I became a physicist, I always wondered, how are those birds not fried? How in the world do they walk around the high tension power line? Well, it doesn't matter. They're at the same potential as the power line. Now, if on the other hand they were to touch something else that was at a vastly different potential, then you'd have a large electric field going through and a large electric force. Then you'd have the shock. But as long as they're at the same potential, they're okay. You know, it's kind of like when you go and pump gas. One of the things that the gas stations frown upon is for you to sit in your car while you pump your gas. Again, you are at one potential, and the gas pump and the gasoline's at another potential. And so if you're at the same potential, you're okay. But when you're at different potentials, then that's where bad things happen. Or, you know, I just, you know, my wife's laptop computer just got fried a few days ago, so it's being taken into the shop. And one of the things that, you know, they required you to do was, you know, essentially ground the computer. You know, they want you to do a power drain, they want you to ground it, and then they want you to put it in an electrostatic bag. So the computer was to be put into an electrostatic bag to transport it. And again, they're looking for changes of potential along the way where the computer can come into contact with a potential that's significantly different than its potential, right? So again, it's all about difference of potential. But current is really the primary driver about shock, is how much current is there. Number two is the path taken by the current. Now, your body's resistance, your body has a resistance overall of about 10 to the 5th-ish ohms. Your heart is an electrochemical device. It has a resistance on the order of 10 to the 3rd ohms. So when you have a severe shock, very likely what the current wants to do is the current wants to go from the high potential down to the low potential, which will be the ground. Okay, so your body is a real nice conductor, essentially. It has all kinds of electrolytes and ions. And then your heart has a lower resistance than other parts of your body. So the current is going to naturally want to go through your heart. It wants to seek a nice path from the high potential down to the ground, down through the bottom of your feet, and it's going to likely go through and pick the path of least resistance, which will be through your heart. And so what I always tell students is, I don't care what kind of footwear you wear in my class, except when you're in the lab. I would like, when we're meeting face to face, I would like you to try at all possible to wear thick-soled shoes. And the reason for that is it just frustrates any kind of current that could go through your body if on the off chance that you do get shocked. Hopefully you don't, but I've seen it come close in classes. So if on the off chance you get shocked, it's going to frustrate that current. You don't want to go and give a nice easy path to the ground. So I oftentimes will tell students to do that. You want to do that when you're handling high power equipment, power tools. You go to your garage. For instance, you might be using like a drill or a saw or some sort of power tools. Again, you don't want to be wearing flip-flops when you're in your garage. And your garage has the excessive danger of, you might have it might be damp. It might have rained the day before. Maybe your car got driven in there in the rain, so you got some water, so maybe some dampness on your garage floor. Again, you want to make sure if you're going to go handle power tools, that again, you wear thick-soled shoes and you take the precautions necessary to try to frustrate that current, that easy current going through your body. So again, the path is also very important. That's number 2 for shock hazards. Number 3, the duration of shock. Of course, that seems obvious. The longer you have a shock, the more time there is to do damage to your body. So again, the duration of the shock. And number 4 is the frequency F of the current. And for DC, F equals 0. So it doesn't come into play for DC. But for AC, you have the situation where you can't let go. You have the can't let go issue. As much as you want to let go of the shock, for the AC currents, you have this whole concept that you can't let go. It kind of grabs you. So let's kind of look at some currents, just kind of give you an idea that these currents are not as large as you might think that they are to do major damage. So I'm going to go and share my screen. We're going to look at a table of these kind of currents and what level of current can actually cause damage to your body. So give me a moment here. So I think this is a very, this table I'm about to show you is a table that I think there's, no pun intended, I think has shock value to a lot of students who see it. Again, it's when you're talking about studying electrical phenomena and you're going to actively participate in that, you need to understand this. I'm going to share my screen here right now. And we're going to see a table. This is out of OpenStax. This is OpenStax table 20.3. Now, you look at this table, and the current on the left column is in milliamps. Again, that's 10 to the negative 3 amperes. So if you touch a 1 milliamp current, that's a threshold of sensation. It means you'll feel something. You barely feel something at 1 milliamp. At 5 milliamps, that's the maximum harmless current. That's a current that can touch you and it will not do any harm to you. Now we go to 10 to 20 milliamps. Again, these are milliamps, okay? 10 to 20 milliamps, you have the on state of sustained muscular contraction. You have the cannot let go duration of shock. You have contraction of chest muscles, and you could also stop breathing during the shock. That's 10 to 20 milliamps. Okay, we're constantly doing calculations in the amperes, right? You can easily have 1 or 2 or 3 amperes in a lab. This is 10 to 20 milliamperes, and you already are going to have, you're going to have contracted chest muscles, cannot breathe, and cannot let go. Unfortunately, the problem with AC shocks is that as much as you want to let go, you cannot let go. At 50 milliamps, now you start getting severe pain. At 100 to 300 milliamperes, we're talking about ventricular fibrillation possible. Often at this point, you can die. And that's 100 to 300 milliamperes. You're not even at a third of an ampere. At 300 milliamperes, you have burns, concentration of current, depending upon the concentration of current, you get burns. At 6 amperes, okay, we're jumping all the way to 6 amperes now. Onset of constrained ventricular contraction and respiratory paralysis. Both cease when the shock ends. Heartbeat may return to normal. You use the defibrillator heart. The problem is with your heart is your heart is programmed to beat at a certain frequency. You get this kind of a shock, you may literally erase the programming in your heart. This kind of a shock, you may actually have to have a pacemaker, some device that actually controls your heartbeat for you. So again, this is, you know, most of this scary stuff is at up to about 1/3 of an ampere. Now, very easily in the lab, you can be working with 1, 2, 3, 5 amperes. Okay, your household wiring will usually trip a fuse at about 15 amperes, maybe 20 amperes. All right, so again, it doesn't take much current as measured in amperes to cause severe shock hazard to you. Okay, so I say this, and of course, the other scary part about this, the path, because when you have a shock hazard, the best path through your body is through your heart, because it's going to take the path of literally, no pun intended, least resistance. Okay, and your heart has less resistance than the rest of your body. All right, and so again, this is, you know, the idea of the shock. So again, 2 major hazards that you may come into contact with your body with electricity. One is the thermal hazard, and the other is a shock hazard. Okay, so not to scare anybody, but again, it just gives you a very deep respect for electricity. Okay, so now let's do a couple of I would say a couple of hazard problems, and then we'll leave that particular topic. All right, so I'm going to do OpenStax 20.85. Okay, OpenStax 20.85. That says how much power is dissipated. This is a part A. How much power is dissipated in a short circuit? A 240 volt AC through a resistance of 0.250 ohms. B, what current flows? All right, so how much power is dissipated in a short circuit of 240 volts AC through a resistance of just 0.250 ohms? And B, what current flows? All right, so for part A, average power. P average is VRMS squared over R. And we're looking at thermal hazard here. So VRMS squared, we're probably in the garage where your house, your regular house is 120 volt AC. Sometimes your garage outlets can go up to 240. It's operating power tools, for instance. So 240 volts, 20 squared divided by this little resistance of just 0.250 ohms. And that's going to give you an average power of 2.30 times 10 to the 5th watts. Very, very high power. Probably will cause a fire. Okay, short circuit, this is bad. No device is designed to take in that much power. That's gonna build up a tremendous amount of thermal heating and possibly melt your device and cause a fire possibly. How much current goes through in this particular situation? Well, in this particular case, I can take a look at this and look at the general form of the equation that's always applicable. That's P average is IRMS VRMS. So that means that IRMS is P average over VRMS. Or this crazy power, 2.30 times 10 to the 5th watts, divided by the 240 volts. I find out that the current that is going through my device now because of this is a tremendous 958 amperes. So if this situation's happening, if your house is designed with safety in mind, this will probably never happen because the circuit breaker will say, whoa, very large amount of current. Shut off, shut it down. I mean, I'm exceeding 20 amperes. Let's stop that current right now. Something's wrong. Right? You're likely not even gonna see, if your house is designed with safety in mind, you're not gonna see a 958 ampere current. I mean, you would have a big time blaze. All right, so that's a thermal hazard. Now let's do a problem on the shock hazard. I'm gonna look at 20.88. Open stacks. 20.88. That one says, while taking a bath, a person touches a metal case, or the metal case. A person, bather, touches the metal case of a radio. The path through the person to the drain pipe and ground has a resistance of 4,000 ohms. What is the smallest voltage? On the case of the radio. That would cause ventricular fibrillation. So remember, you get enough of a shock, your heart stops. Okay, so while taking a bath, the person touches the metal case of a radio. The path from the person to the drain pipe and ground has a resistance of 4,000 ohms. What is the smallest voltage on the case of the radio that would cause ventricular fibrillation? All right, so let's look. We're going to have to kind of use that table of shock hazards to kind of look at this a little bit. So, all right. So, how do we do such a problem? Well, we go with Ohm's law. So VRMS is IRMS times the resistance R. Okay, we're given the resistance. We're told the resistance from through the person to the drain pipe to the ground is 4,000 ohms, which is actually good news for that person. That's a pretty high resistance, so the person's probably going to be okay. So according to the table, according to OpenStack's table 20.3, ventricular fibrillation occurs for currents between 100 milliamperes to 300 milliamperes. So again, we want the minimum, so we'll pick 100 milliamperes, right? So I min is 100 milliamperes. That's what I want to use. So again, I know the resistance. I want to pick the current that's going to be the minimum current to cause defibrillation, ventricular defibrillation. So in that particular case, then I would just simply employ Ohm's law. So V, we'll just say V equals IR. Not worry about the DC here. So V is going to then equal I, 100, again, you have to use base units, so 100 times 10⁻³ amperes, times the 4,000 ohms. That means that voltage, minimum voltage, I guess I'll call it Vmin. Vmin will then be 400 volts. So likely you're okay, because I would not expect 400 volts potential difference between you and the radio middle case. So again, and what saves you is this relatively large resistance. Okay, so now going back to circuitry, I mean, again, that was kind of a dark and gloomy discussion of hazards, electrical hazards. But again, anybody who's going to partake in electrical phenomena needs to greatly respect electricity. And electricity is one of those things that can actually, kill you if you, and it can do it very quickly if you don't respect it, and you may not even know what's coming. And so that's why you got always, when you're in the lab, you always got to know where your hands are, what you're touching. Are there any kind of bare wires any place? These are all things. When I'm doing electrical labs, I'm constantly walking around and looking and watching and observing. So these are all things that I'm watching the hands of all the students, making sure they're not touching things they're not supposed to be touching. So again, I'm usually not that hawkish, but I'm particularly careful because I don't want anybody getting hurt. So now we're going to leave that topic and we're going to go on to circuitry again. Now, we've been talking about now our second circuit element, in the past. Now again, OpenStack's actually, what we're covering in chapter 20, OpenStack's actually covers that in chapters 20 and 21. So 21 is actually a relatively smaller chapter, but so we're going to start seeing references to OpenStack's chapter 21 now. Okay, so now if you go back and so the circuit elements that we're going to cover in this class. what can we put on a circuit? Well, we talked about capacitors, resistors, and later on, we talk about magnetism, we'll talk about inductors. So we can put a check mark next to capacitors. We can now put a check mark next to resistors. We covered both of those. And remember, when we talked about capacitors, we actually talked about the concept of connecting them in series and in parallel. Now you can do that with any of your circuit elements. Now I've kind of discussed what it means to connect circuit elements in series and parallel in the previous chapter. So we're going to now show this for resistors. So we're going to connect resistors now in series and in parallel, and we see that we can have a more complicated circuitry involving resistors at this point. All right, and so another pen. All right, so at this point we want to connect resistors in series and in parallel. So again, it's going to be a very similar topic that we discovered in toward the end of chapter 19. So connect resistors in series and in parallel. All right, so first of all, let's talk about series. All right, so remember when we talked about connecting elements in series, we're doing it along the same. What I talked about in the past, I didn't actually have the vocabulary for current yet. I talked about along the same common path, right? So now that we understand current, I can revise my definition of what I'm talking about with series. So when you talk about connecting something in series, circuit elements are connected along the same current path. In the circuit. So what's that? So what does that mean? Well, let me connect three resistors. I'll call them R1, R2, and R3. So I have a battery, again, and again, this is the negative terminal, and there's a positive terminal on my battery or my power supply. As I go along, I'll have a resistor and another resistor and then a third resistor. And I'll call it R1, R2, and R3. And I'll call my battery V. I'll say it has a potential V across it. Now what's going to happen is, again, like anything, if you apply a battery to circuitry, what's going to happen in the battery is the battery has a potential difference of voltage across the battery terminals. I've said this multiple times. When there's a voltage across battery terminals, that generates an electric field. Electric field, of course, goes from negative to positive. You're going to have an electric field that's going to do what? Well, there are available charge carriers, many available charge carriers in conductors. Those free charges are then, because force equals Q times E, those free charges experience a force, and they're pushed along the current. Or they're pushed along the wire, and they create moving charges. We call that a current. So we have a current I, a common current I, that goes through this wiring. And again, as you notice that these resistors are all connected along the same current path as I move along this wiring. These resistors are then said to be connected in series. I could rip out all the resistors and put in capacitors. I could put a capacitor C1, capacitor C2, capacitor C3. And I would again say that those capacitors are connected in series. any circuit elements that are connected along the same current path are connected in series. Now, with capacitors, I had to watch my words a little more carefully, and I said that the capacitors were connected along a common branch in the circuit. We did not know the word current yet. That didn't come until chapter 20. Now I can relax a little bit more, and I can actually state what the true definition of a series connection actually is, and that is along the same current path. Well, if that's the case, I know by the conservation of energy, remember, voltages are just energy divided by charge. Charge is nothing but a scalar value, and so you're going to divide a scalar by another scalar, you get a scalar. So when energies are conserved, so are also potentials. So I literally can say, as I go along, and I'm going to talk about generalized what are called Kirchhoff's rules later on, but in general, if I apply the conservation of energy, again, it's going to be applied in terms of potentials. So conservation of energy applied for potentials, I would say that the potential generated across the battery has got to equal the potential drop across each resistor. Every single time a current goes across a circuit element, it experiences what's called a potential drop. So you have a potential rise across the battery, and every single time there is a circuit element gets crossed, the potential drops. And eventually, by the time it gets back to the battery, it's at zero. We'll call this Kirchhoff's loop rule. I mean, again, we don't know about that yet, but that'll be what we'll talk about in a moment. That is an official rule due to Gustav Kirchhoff. All right, so Kirchhoff's loop rule is going to say that every single time I cross, I'm going to drop in potential every time I cross the battery. So it means that this is going to balance out. So V is going to have to equal V1 plus V2 plus V3. So I'm going to drop in potential V1 across resistor 1. I'm going to drop in potential V2 across resistor 2, and I'm going to drop in potential V3 across resistor 3. And by the time I get back to my starting point, I'm back to zero potential. So I'm going to utilize this. I know that V1, so V is V1 plus V2 plus V3 for potentials in series. And I said the exact same thing when I talked about capacitors. All right, so for realistic purposes, let me erase this picture. All right, and so I know that for capacitors in series, again, I'm talking about series, that the potential across the battery is going to be the potential drop across resistor 1 plus potential drop across resistor 2 plus potential drop across resistor 3. So that means that I can say, okay, well, I know that potential drop across the battery. Well, so we're talking about resistors. So what is the rule for potential calculation for resistors? Well, it's Ohm's law, right? In general, V equals IR. So if I have a current I and I'm going through resistor R, there's going to be a potential drop of V. That means that I would say, okay, well, that's going to be every single resistor is going to have the same current going through it. So IR1 plus IR2 plus IR3. Every single one of these resistors is going to have the same current going through it. That's the whole point of being connected in series, is that the current going through the various circuit elements is common. What I can do algebraically is extract the I in front. So V is then going to be I times 20 R1 plus R2 plus R3. And I actually can say, well, I can actually refer to this as R sub series. I can add them up and say, well, that's IR sub S. I can add up all resistors. So I can actually take that original picture that I drew and replace it by a single resistor. So instead of drawing the original picture that I drew, again, I talked about this with capacitors as well. Remember my battery, and I drew 3 resistors in series. R1, R2, R3. There's a battery that has a potential across it of V. And there is a common current I everywhere. This is my previous picture, but in miniature thumbnail form. All right. What we're saying is that instead of having these three resistors in series like this, I have just as well. I can make an absolutely equivalent circuit by just having one resistor. And that resistor has a resistance of R sub S. I'm going to stick it over here, for instance. So I'm ripping out the three resistors, and I'm going to put in one resistor with resistance R sub S. That is an equivalent circuit. This absolutely equivalent circuit, and I'll have this current I going through it. Absolutely equivalent circuit. So instead of having the three circuits in resistors in series, I actually can make an equivalent resistance. So in fact, the equivalent resistance of resistors in series is literally R. I put S for series. It's going to be R1 plus R2 plus R3. And if I have multiple, I can just go plus dot dot dot. I mean, if I have more resistors, if we have resistors that are connected in a series, you can give yourself an equivalent resistance. You can, instead of having all the resistors connected in a series, I instead can replace it, substitute all those with just one resistor. And that resistor has the resistance given by the sum of all the resistors that are connected in series. That is called connecting in series. Okay, and I discussed that with capacitors. Now, I also have the possibility of connecting in parallel. So instead, and a lot of the wiring in your house is connected in parallel. When you hook up a lot of appliances on the same circuit, those circuits are usually connected in parallel. So now we're going to connect resistors in parallel. And again, I discussed this with the first circuit element we talked about, and that was capacitor. Now remember, if I talk about, so here, let me draw a little picture here. I have a battery. And with parallel, what I'm talking about is I have an equipotential. My wire is an equipotential on top. And I will connect resistors between one equipotential and another. And I connect them what is called parallel. Now, this is why the study of equipotentials is so important. Because I'll say this is resistor R1, this is resistor R2, this is resistor R3, and I'm going to use the same battery as I did before, but now I'm going to take my resistors and I'm going to connect them differently. I'm going to connect them what's called parallel. And here's why this is important. This upper wire up here is an equipotential at one particular potential. We discussed that in chapter 19. This wire in the bottom is another equipotential. So there's a potential difference or a voltage across the battery. Well, again, these 2 points are at the same potential difference, which means that this equipotential is at one potential, and this equipotential at the bottom is another potential. That means that each of these resistors has the same potential across it, because they are the difference of the same equipotentials. Remember, a conductor is an equipotential. So that means that the potential across each of these resistors is the same, and it's the same as the potential connected across the battery when I connect things this way. All right, and so when I connect things this way, I have to look at things a little bit differently. What I now have is I have a current that's going to be generated. Again, I'm connecting across a battery, so I'm going to develop an electric field, which is going to cause force, is going to move charges and create a current. Now, this is what's different. The current approaches what's called a junction, which is a decision point. The current's like, well, let's see. I either can go through path 1, path 2, or path 3. Which path should I choose? Well, the current is going to choose paths based upon the resistance. And so what you're going to find out is that you're going to actually have a current, oh, there's R1 here. You have a current I1 that goes through path 1. You'll have a current I2 that goes through path 2. Again, this is a junction. The current has to make a decision. And you'll have a current I3 that goes through path 3. All right, so the parallel arrangement of resistors. So first of all, each resistor, let me kind of summarize what I just said. Each resistor is connected across the same equipotentials. Which is also true for the battery itself. So they all have potential difference V. Across them. Right? That's the first thing. All right. And then the other one is by the conservation of charge. Again, that's another conservation law. By the conservation of charge. And all current is charge flowing per unit time. So by the conservation of charge, the current I from the battery approaches a junction, as it's called, formed by the parallel resistor combination. Causing the current to split up. All right, and it splits up in the following way. So again, all of these potentials are the same because they're connected across the same equipotentials when I connect in a parallel arrangement like so. And then by the conservation of charge, a decision has to occur for the current. All right, so the main driving equation for the parallel arrangement is again is a conservation of charge. And so when I talk about applying a junction, the main equation that's going to be applying here is going to be simply that I, the total current from the battery, is going to be split up. And I mean, again, I can't charge is neither created nor destroyed. So it's going to have to be I1 plus I2 plus I3. Well, again, what do we know about current going through resistors? Well, again, we have Ohm's law in general. V equals IR, right? And so what this would then say is, I always want to talk about potentials. And so instead of I can write I as V over R. So in this arrangement, I can say that I is going to be V, again, the same V over R1 plus V over R2 plus V over R3. Or I can extract V out and I can say that I is going to equal V times the quantity, 1 over R1 plus 1 over R2 plus 1 over R3. All right, so what I'm seeing here is I can actually imagine that instead of having these three resistors connected in parallel, I actually can substitute it also for a single resistor. And what would that be? Well, that would be some V over R, and I'll put P for parallel. And again, if it's a single resistor, it is also going to have the same potential V across it, right? Because it's going to have to equal that of the battery. So again, V over 1 over R times 1 over R1 plus 1 over R2 plus 1 over R3. My V's cancel out. So interestingly enough, I have to add the resistors in this weird way that if I want to make an equivalent resistor, the parallel R sub P, the resistor that would substitute in to replace these three that are in parallel, I'd have to calculate them as follows. 1 over R1 plus 1 over R2 plus 1 over R3 plus, if I had more resistors connected this way, I would just keep on going. So what do? I add up all of their inverses. And then when I have that summation of all inverses and I flip it upside down to give you what the corresponding parallel resistor would be. All right. Now, we've seen formulas like this for capacitors, and the weird thing about it is capacitors, so resistors in series add like capacitors in parallel, and resistors in parallel add like capacitors in series. So if you remember, it's funny situation here, and that's just because of the way, so remember when we talk about voltage drops across circuit elements, remember for resistors, it's B equals IR, right? And so we see that the resistance is directly proportional to the voltage drop. But what's the rule for capacitors? And we'll put a little R here, reminder, that's the rule for resistors. The rule for capacitors, put a little C for capacitors. Well, it's the important unit now, or the important physical quantity is not the current, the charge per unit time, but it is now the charge. Remember, capacitors, their job is to store charge on the capacitor plates or the capacitor surfaces. So they actually are Q over C. So the voltage across the capacitor is inversely proportional to the capacitance. All right, and so you'll notice that because of this differing formulation of how do you calculate the voltage drop, you have a difference in formulas. And so again, we're talking about, I'm just going to summarize here with kind of compare and contrast. If you're talking about series, if I take resistors in series, I get them by R. I'll put a little R for series. And we add it the easy way. R1 plus R2 plus R3 plus ... If it's capacitors, we do it the hard way. 1 over capacitor series is 1 over C1 plus 1 over C2 plus 1 over C3 plus ... Again, capacitor resistors in series, so capacitors in series add like resistors in parallel, so on and so forth, right? In parallel, it's the opposite. Parallel resistors we have to add the weird way. So 1 over R sub P is 1 over R1 plus 1 over R2 plus 1 over R3 plus ... that way. However, capacitors in parallel add the easy way. Capacitors in parallel, C1 plus C2 plus C3 plus ... So it gets a little confusing. In that, you're talking series. A lot of times people study resistors first and they say series. Oh, series. That's the easy way. C1 plus C2 plus C3. And then they forget that, oh, wait, capacitors, they add that the other way, right? And so you have to remind yourselves here that if you're adding capacitors and resistors in series, it's the easy way, whereas capacitors in series is this 1 over inverse way. Parallel, well, now the resistors have the hard calculation, the capacitors have the easy calculation, right? And so again, you have to remind yourself of that. And again, it's the concept though of how you obtain these formulas is the same. Capacitors are always along, series is always along a common current path, whereas parallel, it's always designed in such a way where you create two equipotentials you connect across the same equipotential. All right. So I think the one way to kind of look at this is to kind of run some examples here. So let's work some problems from OpenStax. All right. I'm gonna look at OpenStax 21.1. And we're still in chapter 20 in our stuff. Your current book has decided to throw all this into chapter 20, where OpenStax put it into 2 different chapters. All right. So A, what is the resistance of 10 275 ohm resistors? Connected in series and then B, we want to do it in parallel. All right, so 10 resistors. So in series, remember, it's just what? R1 plus R2 plus R3 plus ... right? All of these resistors, however, have the same resistance. So really would get down to as simple as this, is just 10R. I just have R plus R plus R plus R plus R 10 times, right? So it's gonna be 10R. So the resistance is 275 ohms. So it's just gonna be nothing more than 10 times 275 ohms. So altogether, the series resistance would be 2,750 ohms. Move the decimal place. But now, what if they're connected in parallel? Well, in parallel, well, what's parallel again? 1 over R parallel is 1 over R1 plus 1 over R2 plus 1 over R3 plus ... Well, in this case, all the R's are the same, right? So I would have 1 over R parallel equaling 1 over R plus 1 over R plus ... 10 of these, right? And so I'd actually have 10 over R, right? And so what would that do? Well, again, when I add them all up like this, I don't get the resistance. I get 1 over the parallel resistance. When I get done doing this whole sum, I got to flip them upside down to get the actual parallel resistance. So again, the parallel resistance then becomes R divided by 10. Or 275 ohms divided by 10. So my parallel resistance, I hook up all these same resistors in parallel, my total resistance now becomes just 27.5 ohms. Okay, so the thing to keep in mind is that when you connect resistors in parallel, the total resistance is smaller than any of the resistors involved. I mean, that's what I said about capacitors in series. Remember, you connect capacitors in series, total capacitance is smaller than any of the capacitors involved. Well, that same statement is now true for a parallel, an overall parallel resistance. So again, I just demonstrated that. This RCP is much, much smaller than any of the 275 ohm resistors involved. And so again, remind ourselves of this statement again. Just remind you. So the total capacitance of capacitors connected in series is smaller than the capacitance of any of the capacitors involved. I make that same statement for resistors, but for parallel. So I can just go to like copy paste the total resistance of resistors connected in parallel is smaller than the resistance of any of the resistors involved. We saw that with the last calculation. You connect a bunch of resistors in parallel, you'll get a smaller resistance. All right, let's look at OpenStax 21.4. All right, that says an 1800 watt toaster. A 1400 watt electric frying pan. And a 75 watt lamp. Are plugged into the same outlet in a 15 ampere 120 volt circuit system. Okay. The three devices are in parallel when plugged into the same socket. All right, so the three devices are in parallel. When plugged into the same socket. Okay, A, what current is drawn by each device? What current is drawn by each device? B, will this combination blow the 15 ampere fuse? All right, so we have a bunch of appliances plugged into the same circuit here. So an 1800 watt toaster, a 1400 watt electric frying pan, and a 75 watt lamp are plugged into the same outlet in a 15 ampere 120 volt AC circuit device. The three devices are in parallel when plugged into the same socket. A, what current is drawn by each device? And B, will the combination blow the 15 ampere fuse? Well, you have an overload. All right, so there's a safety fuse. And all right, so let's all All right, so let's remember these numbers and let's work this problem out here. So all right, part A. All right, so what we have to do is we know that the so I'm gonna let T stand for toaster, FP for frying pan, and L for lamp. All right, so I'm going to use these various subscripts, and when I do that, I want you to understand that when you see a capital T, that means toaster, FP means frying pan, L means lamp. I have a lot of things going on here. All right, so the power of the toaster, we're told is 1800 watts. Okay, the power of the frying pan, the power consumption by the frying pan, F piece of FP, we're given that's 1400 watts. And the power consumption by the lamp, we're told that we're given that's 75 watts. Great. The voltage out of the wall is 120 volts. So again, by Ohm's law, we can essentially understand that these are all basically we can consider. Let me back up one here. Appliances connected to a circuit are considered like resistors. So when you apply a light bulb or a toaster or frying or electric frying pan, whatever, that's like putting some big resistor that's gonna dissipate a bunch of heat power in your circuit, right? And so we know then in that case we can use Ohm's law, so we can use Ohm's law at this point. And essentially, instead of saying, well, let's say for instance I have P toaster, well, I can always write that that's going to be I toaster V. And again, they're connected in parallel, so they're all going to have the same V. Okay. And so I would then say, well, that's going to be I toaster will be P toaster divided by V, or 1800 watts divided by 120 volts. And that's going to be 15 amperes itself. Yeah, we use the same V because of parallel connection. We're going to use the same V across all these other calculations. So I can do the same thing. I say, okay, well, I frying pan, I sub FP. Frying pan, I was told, is 1400 watts. Divided by 120 volts. That implies that the current in the frying pan, electric frying pan, I do that calculation, is going to be 11.67 amperes. And I can do the lamp, the current in the lamp, again, same math. This time it's 75 watts divided by 120 volts. That implies that the current in the lamp will then be 0.625 amperes. So part A is asking me to to state what is the current drawn in each of these devices. Well, the current drawn in the toaster is 15 amperes. The current drawn in the electric frying pan is 11.67 amperes, and the current drawn in the lamp is 0.625 amperes. I mean, that is the answer to part A. The answer to part B is, well, will you blow the fuse? Well, if the combination of these devices exceeds 15 amperes, then yes, you'll blow the fuse. I mean, I pretty much have blown the budget. I mean, I can look at this really quickly right now, and I've blown the budget practically with the toaster. Anything above the toaster is going to blow the fuse. I have an overloaded circuit. But let's be official about it. So let's remember these numbers. This is the answer to part A. Let's remember these numbers to determine whether we blow the fuse. Remember, the fuse gets blown if the combination exceeds 15 amperes. So again, the combination is parallel. The combination is connected in parallel, and we're looking at B. All right, in parallel, which means that the currents must add. So the total current in my system is a current for each of the resistors in this parallel combination added up. So it's going to be I toaster, that's one branch of the current, plus I sub frying pan, that's another branch of the current, plus I sub lamp is another branch of the current. So the total I is going to be 15.0 amperes plus 11.67 amperes plus 0.625 amperes. So the total combination of currents in the system, you add that up, is going to be 27.3 amperes. Well, I equals 27, so that's my answer. I equals 27.3 amperes is greater than 15 amperes. So this combination will blow the fuse. The fuse is set to detect if there is ever a current greater than 15 amperes. If a current in your system is greater than 15 amperes, then your fuse will be blown, and this is a dangerous combination. So you clearly see if you hook up these three devices like this, you'll draw a current of 27.3 amperes, which is unacceptable. And so that will exceed the 15 ampere threshold and blow your fuse. Okay. Let me look at example 21.6, and that's a very good example. That's going to have a lot of cool things in it. So, which I didn't really see any of the OpenStax problems being at the same level as example 21.6. So I'm going to kind of run through that example. This is more of a complicated combination of resistors, but let's kind of see how this works. All right. So I'm going to look at it. So I'm not looking at a problem now. I'm going to look at an example 21.6 out of OpenStax. This will be OpenStax example 21.6. I want to work through that. All right, so what it says is find the total resistance, and it's going to give you a combination. So find the total resistance. And then B says, what is the IR drop in R1? Again, none of this makes any sense until you said figure. What is the IR drop in R1? Okay, and then C, find the current I2 through R2. D says, what power is dissipated in R2? All right. This is an example that's going to give you a lot of physics in here. What is it? What power is dissipated in R2? All right, so great. So what am I even talking about? Well, I have a schematic. I have a battery, voltage V. I have a resistor right here called R1. And then I have a parallel combination of resistors. Down here, I'll go branch off. I'll have R2. And over here, R3. They come back together. Then I finish the circuit. All right, so let's kind of walk through this. And again, we're told what these R's are. R1, I'm still on the camera here, barely. So I'm trying to economize here. So R1 is 1.00 ohms. Okay, R2 is 6 ohms, 6.00 ohms. R3 is going to be 13 ohms. And the battery has 12 volts across it. So 12-volt battery. All right, those are my resistors. And what I want to do first and foremost, all right, so doing circuit analysis is generally complicated, right? And so here's the idea here, is that, okay, so I know going out the battery, there's going to be some sort of an I1 that'll occur. So there's a current that's going to come off the battery. Call it I1. Now that I1 is going to go through R1. Now, if I had a corresponding parallel, if I was able to instead, combine these two resistors in a parallel combination as one resistor, well, that one equivalent parallel resistor would also be connected in series to R1. It would also have I1 across it. But the way it's connected right now is that I1 approaches a junction. Okay, because R2 and R3 are connected in parallel. So I1 approaches a junction. It's going to have to split up. It's going to have, let's say, I2 going through R2. And it's going to have I3 going through R3. And then it comes back together and becomes I1 again. Back to the battery. So here's the thing. If you look at this, it's going to want us to, so when you do circuit analysis, we first of all synthesize, and then we analyze. Right? Synthesize means put it together. So oftentimes there's no way I can know anything unless I get an equivalent resistance and figure out what I1 is. So here's what we're going to have to do. We're going to have to take this whole combination and make an equivalent resistor so that I have any idea what I1 is. At this point, I can't solve this problem. So I need to synthesize to an equivalent resistor, using the concept of parallel and series resistors to give me I1. And once I know I1, then I can sit there and say, okay, now I want to figure out what I1, so I1 is going to go through an equivalent parallel resistor I can call R23. If I know that current, then I know the voltage that goes across R23. And I know that voltage will be the same as the voltage across each of these parallel resistors. Then, once I know the voltage across each of the parallel resistors will be the same, then I can solve for I2. Because why? Well, first of all, I want to know the IR drop across R1. I'll do that earlier on, but I want to eventually find what is I2. I have no way of doing that right now. And then finally, I'll figure out the power dissipated in R2. So again, the point is going to be, I'm going to have to synthesize the circuit to create an equivalent resistor. And then I'm going to have to analyze means to take apart the circuit, basically unravel it again to get inside and get the information about a particular internal resistor that's inside of a parallel combination. All right. So again, this is the process. This is not an overly complicated problem, but there's gonna be some ugliness to it. And so I will warn you. I mean, that's the way these circuit problems are. All right. So let's I'm gonna try to I need to analyze real estate. I'm gonna do number one. I'm gonna do first of all part one. And unfortunately, it becomes very difficult to do this when I have so little whiteboard space, right? So I want to try to. So you have to kind of keep careful notes here. So, so again, I really would like to try to reference various pictures, various equivalent circuits when I do this. So let's kind of do this one step at a time. First, I need to synthesize. All right. So I'm going to talk about the first original circuit. I have an R1. And I'm going to try to draw this a little bit, almost like small. It's going to be, it's going to be one of those things you're going to have to kind of do it with pictures. All right, so there's R1, and then I split up into R2, R3, and I come back together, and I finish the circuit. Here's my original circuit. All right, now I have V, I have R1. And as I said before, I expect an I1 through R1, and it's going to have to divide up as I2 and I3 through R2 and R3 respectively. All right, again, it's a little bit small. Okay, I have no idea how to do this problem at first. I have to synthesize. So I got to redraw this. I will call this picture Roman 1. I'll call this Roman numeral 1. That's my first stance of this equivalent resistor. Now, I want to synthesize it, and I'm going to unravel it, right? So I'm going to do now is make what I call Roman numeral 2 picture. And how I'm going to get that is I'm simply just going to combine the parallel resistors. All right, and so I draw this battery again. Here's my battery. I don't touch R1, but now I'm going to create what I'm going to call R12. So here's R1, R23. Now R23, when I create this and I do this parallel combination, what's gonna be interesting about it is that it's gonna have the same I1 going through it, because it'll now be connected in series. Okay, now, and then finally, what I get is I'll get Roman numeral 3 when I notice that these two resistors are connected in series, and I can just add them. So then my final picture looks like this. I have a single battery, and all I have is one resistor on it. And this particular current has just I1. This is my R total. Little T for total. Here's my battery. All right. So that's what I'm after. I'm going to go from our Roman 1 to Roman 2 to Roman 3. This is my series of pictures. I combine these two resistors in parallel to give me R23. And now I know R23, R1 and R23 are now connected in series. They simply just add to give me R total. Now what's left is to give you the details, right? And so let's make a little parking lot of stuff that I know. And I'll just so I know what these various resistors are. Again, as I wrote this down, R1 is given to us as 1.00 ohms. R2 is given to us as 6 ohms, 6.00 ohms. R3 is 13 ohms. And the voltage across the battery is 12.0 volts. All right, I have some calculations to do. First of all, I have to figure out what R23 is for picture number Roman 2. How do I figure that out? Well, remember, those are resistors in parallel. So 1 over R23 is going to have to equal 1 over R1, I'm sorry, 1 over R2 plus 1 over R3. Okay, to give myself the equivalent parallel resistor that represents these two resistors, R2 and R3, connected in parallel, I have to add this weird way, remember. So let's do that. So 1 over R23. What's R2? It is 6 ohms. So that's going to be 1 over 6 ohms plus 1 over 13 ohms. All right, so I'm going to kind of do things slow motion using my calculator here. 1 over R23. Again, you have to get used to adding like this. This is a really weird way of adding. So I grab my calculator. I'm going to add 1 over 6 plus 1 over 13. When I do that, I'm going to get something that's going to, I'm just going to kind of write down what I have in my calculator. When I do that, I'll get 0.2435. This is my calculator readout. 897436. Again, I'm doing this for you because I'm expecting that you're doing this also, and that if you get this number in your calculator, then you did it right. But again, that's not the number I want, is it? Because I just calculated 1 over R23. I want R23. So I'm going to take this number and turn it upside down. So I take this number in my calculator and I'll hit the R to the negative, or I'll hit the X to the -1 button. I'll flip it upside down. When I flip it upside down, what I get is 4.11, or actually it's 4.105. I'll reduce it as, so my R23, when I invert this number, I'll get about 4.11 ohms. All right, so again, 1 over R2 plus 1 over 3, 1 over 6 plus 1 over 13 is going to give me this readout. But again, that readout is 1 over R23. I want R23, so I'm flip it upside down and I'll get 4.11 ohms. Great. So that's another piece of information that I need. R23 is 4.11 ohms. Wonderful. So now I know that. That's information I need for Roman numeral 2 picture. But now I have the Roman numeral 3 picture. How do you get that? Well, once you've done the parallel combination, you got R23. Now what you have is R1 and R23 that are now connected in series. They're connected now across a common current I1. And what's nice about that is they add the easy way. So to get our total in Roman numeral 3, our total is literally nothing but R1, I'll finally involve R1, plus R23. That's the easy way. Our total is going to be R1, which is just 1 ohm, plus the 4.11 ohms. Our total will be 5.11 ohms. Fantastic. I now have calculated all the information I need to support my pictures. So our total in picture Roman 3 is 5.11 ohms. All right, there you go. So now let's start answering the questions. I have all the information I need to answer the question. So the first question that I need to answer requires me to have done the full synthesis. It means synthesizing all the way from Roman 1 to Roman 2 to Roman 3. The first question, to remind you, the first question says, find the total resistance. There it is. That's the answer to the first question. So the answer to the first question, part A, it's right there. There's your part A answer. Total resistance 5.11 ohms. Okay. Now, part B. Okay, so I had to go through all of that, combining in parallel, combining in series to give you the total resistors. This is the resistor that instead of having this combination of a series combined in R1 in series with a parallel combination, I could have just ripped all that out and got a resistor of 5.11 ohms and did this instead. each of these pictures is an equivalent circuit. They're all equivalent. All right. Now, I have to do the full synthesis to be able to answer part A. Synthesizing means getting them synthesized to one single resistor. Now, what is part B asking? Part B says, okay, find the IR drop in R1. Now, remember, when you have a resistor, it's called a voltage drop. Sometimes because V equals IR, this is more slang. They'll call it the IR drop, if you will, but it is the voltage drop. Again, a current going through a resistor or a current going through a capacitor or any circuit element is going to experience a voltage drop. All right, and so that's what it's asking for. So how do I figure that out? I want the IR drop. I want the voltage drop across R1, which is going to require me to use picture Roman 2. But I have no idea what I1 is. So I need to go to the most synthesized picture, which is Roman 3, to get I1. Well, then it becomes easy, right? Because the voltage across the total voltage, again, it's going to be I1 R total. I have to, in order for me to get the voltage drop across R1, I have to know I1. But I can't know I1 from this picture. I have to know it from this picture, the most synthesized picture. Well, then it becomes easy, right? Because now I1 is simply V over R total, or the voltage across the battery, 12.0 volts, divided by R total, which is 5.11 ohms. So then I1 off of Roman 3, I1 is going to be I1 is going to be 2.35 amperes. Great. Now that I know that, and again, I got that value by looking at picture Roman 3, I'm now going to start analyzing or unraveling. I'm now going to unravel back to Roman 2. So I'm going to unravel from Roman 3 to Roman 2. And what I now know is I1, and I now want to know the particular voltage drop across R1. Well, that's simply going to be V1 is I1 R1. And I know I1 from my previous calculation looking at Roman 3. So now it's going to be simply 2.35 amperes multiplied by 1 ohm. So the voltage drop across V1 is going to be 2.35 volts. All right. So again, so part B's answer. This is part A's answer. Part B's answer is going to be that voltage across 1 is 2.35 volts. Again, I had to fully synthesize the problem and unravel it back to Roman 2 to get that. Okay. What's the next question asking? Next question says, okay, find the current I2 through R2. All right. So now I'm going back to the original picture. I'm going to unravel one more time to picture Roman 1. But I can do that now, right? Because I know what I1 is. I know that I1 goes through R1. I1 also goes through R23. And if I know that I1 goes through R23, I can figure out the voltage across R23, which has to be the voltage, because they're in parallel, these are in parallel, that has to be the voltage across 2 and the voltage across 3. Once I know the voltage across 2, I can find I2 through Ohm's law. Again, I have to unravel one more time. All right, so let's do that. So I want to find information particularly about what's actually going across that one resistor there, R2. So again, I can't do that problem unless I know I1. So in order for me to know I1, I had to unravel, I had to synthesize all the way to here, and then I have to unravel back to know to look at Roman 2. So by Roman 2, okay, we know that I1 passes through R23. We know that. All right. So B23 will be I1 R23. I can now find the voltage drop across R23. Let's do it. I1, 2.35 amperes. I calculated earlier. R23 is going to be 4.11 ohms that I calculated earlier. And it's up here in my parking lot. V23, when I run through that calculation, it's going to be 9.66 volts, which is the same voltage across R2 and R3 because they are connected in parallel. Okay, so I'm gonna unravel. So now when I eventually unravel back to the original picture, Roman 1. Now I know that because I know I1, I know what the voltage is across R23, which, by the way, since R2 and R3 are connected in parallel, that's also the voltage across R2 and also the voltage across R3. So what I now can do is unravel one more time back to the original picture. Unraveling back to the original picture means I can now directly talk about R2. All right, so now I know that this voltage is going to go across R2. So let's go perform the next calculation. And this is a lot easier when I have a lot of whiteboard space. All right, so V23, I particularly care about R2 right now. So V23, which is equal to 9.66 volts, passes through, or I'm sorry, not passes, is across R2. Great. So I know what R2 is. I know what V23 is. I can again use Ohm's law. V23 is I2 R2. Okay, and I can find I2, which is what I want. So I2 is V23 over R2, or the 9.66 volts divided by R2, and R2 is 6 ohms, 6.00 ohms. That means that I2 is going to be 1.61 amperes. That is the answer to part C. Fantastic. 1.61 amperes. I have unraveled now, so we have unraveled to Roman numeral 1, right back to the original picture. I have to synthesize the Roman 3 and unravel the Roman 2, then unravel the Roman 1. All right, so there you go. I2 is now 1.61 amperes. Just put that on my little list of answers now. And then part D is not going to is going to be the easiest because now, so part C's answer is I2 is 1.61 amperes. Finally, we want the power dissipated by R2. How do you figure that out? Well, that's a pretty easy to do now because I can now say, oh, I want power dissipated across R2, so that's going to be power dissipated across R2, called P2. Again, what is that? It's I squared R heating, right? So it's I2 squared R2. I know everything now, I can do this. So power across R2 is going to be this 1.61 amperes squared, and then R2 again has a 6.00 ohm resistance. So the power that will be particularly dissipated across little resistor R2, when you multiply and do that, it'll be 15.6 watts. Again, this is not, and this is a part D answer. So this is not the most complicated circuit possible, but the idea is the game that you have to play when you do a relatively, complex circuit or any kind of circuit analysis is that you have to pretty much know anything at all about the problem, to know any numbers at all. You're going to have to fully synthesize the circuit. Right? You have to fully synthesize it, get it all the way to one equivalent resistor. Then once you are able to determine the current through that resistor, then you can start analyzing. You can start unraveling the circuit to previous pictures. So for me to answer question one, I mean, first of all, question one is just what is the total resistance? So I have to fully synthesize to get to the current, the circuit that is only represented by one total resistor. But if I want to know what the potential is across V1, well, that would mean, well, okay, what would that be? Well, V1 is I1 R1, but see, I don't know what I1 is yet. There's no way of me knowing this unless I fully synthesize this picture. I use this picture, Roman 3, I'll get I1. Once I know I1, I unravel back to Roman 2, and I look at this particular circuit, this equivalent circuit, and I can now calculate V1. Then the next one says, okay, you have V1. I want to know what the particular current now is across I2. Well, again, I don't know. So I have to go back to Roman 2 and understand that R23 is connected in series with R1. So the same current I1 goes through R23. So what I now have to do is figure out what is the potential across R23, which I'll call V23, and understand that in a parallel connection, that potential, these potentials, these two resistors in parallel will have the same potential across them. And of course, the current must split. So much current will go through I2, R2, we'll call that I2, so much current goes through R3, we'll call that I3. So once I know what V23 is, I now understand that that is a potential across resistor R2, and now I'm in position to calculate I2 again by using Ohm's law. Now at this point, I pretty much can know everything. And now I can calculate, let's say, power consumption or power dissipation in R2. Well, that's simply I2 squared R2, and I can just directly calculate that because I've now done the pain of actually going through the synthesis and analysis process to actually figure out what are the currents and voltages and all the resistors that comprise the circuit. And that same kind of analysis would occur for a complex system of capacitors as well. Okay, now let's talk about some other topics here that are not as complicated as what we just been talking about before. So again, we're going to I'm going to change now the course of this discussion to really be more laboratory focused. What would we actually see in the laboratory? All right, and so in the laboratory, again, we don't have the benefit of actually meeting face to face and actually going to a laboratory. But again, assuming one day you will, once COVID-19 has been resolved, if it ever does. So let's take a look at some terminology. All right, so I'm going to change topics a little bit here. So this is parallel and series resistors, and this is an example that gives you a feel for how you do this kind of stuff. Now let's talk about the next term I'd like to talk about is what is called electromotive force. Now you'll notice that I have sometimes labeled my battery with an epsilon. You might say that's a funny letter for a battery label. Why would you do that? Well, turns out that if I look at a battery, well, first of all, we're going to analyze power sources. Okay, so first of all, let's kind of talk about your life experiences. All right, so let's say, for instance, as an example, when you forget to turn off your lights of your car. You may wake up the next day to notice that your battery has depleted. Now, what might you notice? Well, you may notice that the lights are dim. So you have a dimmed down lights. So the question really is, why does that happen? Why don't the lights just flick off? I mean, why did they go through this process of dimming? I mean, why doesn't, I mean, when your battery's dead, boom, it's dead, you flick it off. Why would we have this natural decaying of the battery, this depletion of the battery? Or another thing you might notice. Let's say that instead you have a good battery. So let's say instead the battery is good. And fresh. But you overload it. Again, you will see the lights dim. So there seems to be some sort of a function within the battery that causes it to kind of deplete, or and it depends on either like the history of the battery, or for instance, the resistance of the battery, but it also seems to depend on the current that goes through the battery as well. There seems to be kind of somewhat of a complicated phenomenon. And so this gives rise to what is called internal resistance. This behavior gives rise to a concept called internal resistance. That your battery or your power supply itself has a resistance. Okay, and so we look at this concept of electromotive force. The reality is your battery may be rated to be at a certain voltage, but that may not necessarily, that will not be the voltage that the load that you're actually applying to your system. because of the internal resistance. So we get into this concept called electromotive force. All right, so electromotive force, the idea is all voltage sources create a potential difference. And I've said this many times. So again, they create a potential difference, which generates electric field, and charged electric field experience a force and then drives a current. Okay, and that's the way all this works. But on a small scale, the potential difference generates an electric field across the power supply. Okay, free charge or free charges in the conducting wire experience a force F equals QE. And we said this before. Electric field is E, the charge has a Q. Then you put a charge in an electric field, you experience electric force, and this drives the charges. In the formation of a current. Microscopically, and again, I've said this before, but microscopically, that's what's happening when you apply a battery to something. Now, electromagnetic theory, some of the terminology came about before people really understood what they were talking about. And so people actually, what they use is they use the electromotive force as a concept. Now, again, you'll notice I've been applying epsilon to things. The concept or the term electromotive force or many people short it down to EMF, by the EMF is the term electromotive force describes the potential difference in the battery or in the power source. And it's a misnomer. Electromotive force is not a force at all. It's a voltage. Okay, so again, terminology was used before people really understood, and sometimes bad terms stick. All right, and so it has units of volts. Bad terms stick, and this is one of those terms that stuck. So for now and forever, we have this whole concept of electromotive force, EMF, everywhere, when indeed it is not a force. It is a voltage. All right, and so the idea is the electromotive force, because of internal resistance and other things, and you kind of wonder here, so electromotive force is what you actually see rated on your battery. And so it's not what is, so again, the electromotive force is the potential difference across the battery when no current flows in it. No current flows. And as we saw, well, clearly there is, when you try to overload a battery, you're going to see a dimming of lights, for instance. So there is something to do with flowing current. All right, and so we have this concept of called internal resistance. All right, so you might wonder sometimes, you might look and say, well, I don't get it. I see, I can look at a truck battery. A truck battery and a motorcycle battery. Are both rated at 12 volts. They're both 12-volt batteries. Why can't I put the motorcycle battery in the truck? Well, what's the difference? Well, and again, the truck battery is much larger. So the truck battery is much larger than a motorcycle battery. And they're both rated at 12 volts. But you're not going to put a motorcycle battery in the truck. And the idea is, well, why? Well, because the large size of the truck battery it has a much smaller, what we call internal resistance. And when we talk about internal resistance, we oftentimes use a little r. So regular resistance, we have big R. Internal resistance, we oftentimes will use a little r. So now internal resistance is difficult to understand. It behaves in squirrely ways oftentimes. And so, you ask yourself, well, can you compute the internal resistance of a battery? Well, oftentimes you can't. All right, and so as we said, there's a definitely complex way. So internal resistance behaves in a complex way. All right, so there's many factors that determine the internal resistance. It could very well be, it could be something as direction of the current. Maybe the direction of the current depends on what kind of internal resistance it has. The temperature, hot day versus a colder day, can affect internal resistance, and we know temperature does affect resistance. It can even be the history. What's the history of your use of this battery? Or this power supply? A number of complicated factors go into place to talk about the internal resistance. So it is very difficult to really state precisely what the internal resistance of a battery or a power supply actually is. But what's important here is, what is the voltage that actually is being delivered to the device, to the system that you're applying the battery or the power supply. All right, so we talk about what's called now the terminal voltage. So we talk about internal resistance of your battery. We talk about the EMF, but now let's consider what's called the terminal voltage. Put it all together. Okay, so the voltage output of a device. Okay, the voltage output of a device is measured across its terminals, like battery terminals. So again, you take a battery and you apply, you have a positive terminal, negative terminal, that actually gives you what is called the terminal voltage. And so thus, we call this the terminal voltage, because you're measuring across the terminals. All right. But that terminal voltage is not going to be the same as the rated EMF of your battery. And the reason being is you have to consider internal resistance. So if you take a look at what voltage am I actually getting out, the terminal voltage is what voltage you're actually going to deliver to your system. What is the voltage your battery is really going to deliver? Well, it's equal to the EMF of what the battery is rated for. That is the voltage of the battery if no current is flowing through, minus the current flowing through times the internal resistance. Once you start flowing current, now you're going to get less out of the battery than what the battery is actually rated for. And it's going to depend on the internal resistance. So if your battery is depleted, your internal resistance goes up. That means your depleted battery, your battery may be rated at, say, 12 volts, but if your battery is really cruddy and it has, and it's worn out, well, now once you start applying current through it, you're not going to get 12 volts anymore. You might get 6 volts. And so what the actual voltage that you're actually going to read across the terminals is not going to be what it's rated for. What it's rated for is electromotive force, EMF. What you're going to get out is going to be depleted by either a higher internal resistance than you realize, that's because your battery's depleted, or a higher current than you should use because you're overloading the circuit. So again, this IR term that comes out, that is going to cause the problem that you're going to have, or you may not actually get enough voltage out of the terminals to operate your device as you want. You might get dimming lights and things like that. Again, it could very well be that your internal resistance has increased because of the age of the battery, the history, or you're putting too much current through it. All right. So those are two things that you have to come to grips with, and that you're not going to, the voltage across the actual plus or minus terminals of your battery is not going to be what the battery's rated for. You say, I have a 12-volt battery. Well, what they're telling you, AutoZone really should be telling you is that, well, yeah, that's a 12-volt battery. That's your EMF. That is if you don't run any current through it all. That is your perfect idealized battery. But once you start running current through it, then you're actually going to get an output that's across terminals that's less than what the rating of the battery is. All right. And so again, oftentimes when I write out circuits, I'm going to write them out, and I use epsilon. So oftentimes I use the Greek letter epsilon instead of EMF. I think your book uses EMF. In general, most physicists will actually use epsilon to talk about the actual EMF of the battery. Now, if you go in the lab, you might say, well, I have a power supply, it's 12 volts, but to do this job, that might not be good enough. You might want to put a couple of power supplies in series with each other. So what happens if you actually use multiple sources? How does that work? All right, so we now understand EMFs of sources. What if you actually use multiple sources? What if I go into the lab and instead I'll have a couple sources that I'm going to put together, for instance. So I'm going to say, let's and again, how you align them is very important. So let's look at multiple power sources. So what I really want to do sometimes is the following. Let's say one battery is not good enough. Maybe I have to put a couple batteries in. So I'm going to line up and I'll have, let's say, an epsilon 1 and epsilon 2. And I want to basically support some load. I'm going to run something. I'll call R sub load. Well, if you look at this, and if I know what I'm doing, well, I'm going to actually align these voltage sources so that they're in parallel with each other. Notice that, when I go from plus to minus, that's going to be electric field that's going to drive the current upward. And again, it's going to be more driving of the current if I have yet another aligned power source, that's aligned correctly. And so what I would actually do is I'd find out that the total current through this is going to be the following. I mean, each one of these sources, okay, is going to have its own internal resistance. So we'll say this is little r1. And this source right here, it'll also have some internal resistance. I'll call it's r1, this is r2. So each of these sources is not going to be ideal. They're all going to have their own internal resistance. Oftentimes you draw your diagram like that. So this is not a very good looking diagram. Let me redraw this. So again, I wouldn't just draw my battery anymore. I would draw it in connection with its own internal resistance. So I'd have epsilon 1 with R1, and I'd have epsilon 2 with R2. And they're aligned. They're in the same polarity, if you will. They're both going from minus to plus in both cases. They're actually working together. And then I come across and I have R load. And I say, well, what's the current that's going to be going through there? Well, if you work this out, it'll actually be the following. Using Ohm's law, the current would actually be epsilon 1 plus epsilon 2 on top. The two voltage sources would actually add, and on the bottom would be all the resistors. So the internal resistance R1 plus internal resistance R2 plus the load resistance, the resistance of what it is you're trying to actually operate. All right, so they would add up. The two power sources, the EMFs would actually add up, and you divide by the total resistance. What if you mess up? What if instead you put these in backwards? So let's say, for instance, that I have minus or plus, but I don't know what I'm doing. And so what I'm going to do is I'm actually going to put the second one in to basically work against the first one. So let's see. Let me see if I can do this right. Yeah, I'll do minus plus here, but let's say I don't know what I'm doing, and so I'm going to actually connect them backwards. I'm going to connect the second one backwards to how it should be connected. What's going to happen now is that it's going to work against the first one. So the resistors in the bottom will still add, but now what I have is, I think I'm trying to help my cause, but instead I've messed up. I put it in backwards. The polarities are in the wrong direction. So what I'm actually having is the EMFs are actually working against each other. Because let's say I'm a newbie technician, I don't know what I'm really doing. So now they're working against each other. All right, and so you have to be really careful. The polarities, remember, the way the battery is going from negative to positive. The electric field goes from negative, will essentially push this. I mean, again, it goes, electric field is supposed to go downward, but again, it's as if positive charge would go. So it's always going to go off positive charge. All right, and so I could have it backwards, or what I can actually do is I could have a situation where I actually put the two power supplies actually in parallel with each other. So I could do something like this. I could say, well, what happens if I decide I'd like to connect my circuit, but maybe instead I want to actually put a couple of I'll have my load resistor out here. And now what I'm going to do is I want to actually connect the two power supplies in parallel. We'll say they're aligned because I know what I'm doing. All right, so now they're parallel, minus plus, epsilon 1, epsilon 2. Now how do they go? I'm going to have some sort of a current that's going to come out like this. Well, the current is now going to say, well, at this point, remember, everything is about equipotentials. I have a potential, I can say, at A, and there's a potential also at location B. So the same potential difference is going to go across both of these power supplies. So the total EMF, effectively, the total EMF. Let's just kind of imagine that these EMFs are the same to make things simple. The total EMF is the same as each EMF. Because they are connected across the same two potential points. A and B. You might ask, well, why in the world would you want to do that? You're not getting any bang for your buck there. You know, if you have two EMFs, then they're sitting there, they're going across the same 2 points in potential, two equal potentials. What would you gain from that? What I would gain from that is actually a reduced internal resistance. And so I kind of messed up my diagram a little bit. There should be an understood internal resistance in each one of these, right? So I would have, given that I'm saying they're the same EMFs, they would have the same internal resistance R. So the internal resistance, you know, if I just had one by itself, would just be R. What would the internal resistance be if they're in parallel? Well, again, they have to add like parallel, right? So it would actually be like 1 over R parallel. Let me use a little r here for this. What would it be? It would be 1 over R plus 1 over R, or 2 over R. So what I would actually do is my internal resistance of this combination, I would actually take that internal resistance and divide it in half. So it would actually have less going against it. So I would actually be getting more terminal voltage out of this by combining them in parallel. Oftentimes, you know, Ray Benj, who designs any of the labs when we actually meet face to face, Ray Benj will actually say, you know, I don't think you're going to quite do the job with the power supplies you have in class. So if you can't do the job, then why don't you connect a couple of these in parallel, and that'll help you do the job. Why does he do that? Well, why that's accomplished is because he's trying to reduce the internal resistance, so that you get more terminal resistance that goes to your load. All right, so that's what you get from applying multiple power sources in parallel. Again, this is more a laboratory type exercise. Again, in so doing. So again, this is a lot of this we're going to talk about now. It's going to be, you know, a lot of this theory that's being applied to how do you operate in a laboratory. All right, next topic, brief topic, is a lot of you guys are bioscience, biology pre-med majors, and so you might ask yourself the question, well, does nature in biology actually show you know, some animals having electrical properties? And the answer to that is yes. animals actually can be electrical detectors, and they actually can generate electricity as well. So again, I just want to briefly talk about that. In your study of biology, you actually will see animals that utilize electricity. So animals as electrical detectors. All right, so first of all, what's interesting is there are a number of animals the number of animals that both produce and detect electrical signals. And so essentially many fish, sharks, platypuses. That's a plural for that, I don't know. And echidnas, I don't know how to pronounce that. So all of these actually they all can detect electric fields. Generated by prey. So they kind of do what we refer to at Raytheon as electronic warfare. Essentially, using electrical signals for conflict. Like when a war starts, the first thing that happens is you have a war in electromagnetics as well. You have people trying to jam other people's signals, and so essentially, without even knowing, you have an invisible war. You have a war of people trying to mess up other people's electronics and electromagnetic communication. And so we see that in case for animals. Animals will use electric fields to actually that their prey generate to detect them. So that's one thing. You also have animals that generate their own electricity. So let me erase this. You have animals that use electric fields to detect prey. And then you have animals that have electroplaques. So electroplaques, as it's called, electroplaques are flat disc-like cells. And they have so for instance, the ones in the electric eel, the electric eel is covered with them, right? Those in the electric eel, is an animal that generates its own electricity, have a voltage of about 0.15 volts across each one. So electric eel is a very interesting animal. Now, the thing about electric eel can pretty much kill you. Electroplaques are usually generated in an array. So electroplaques are usually located near the head and tail of an animal. But for the electric eel, it's all over its body. So, but for an electric eel, they are all over its body. So let's take a look at the electric eel briefly. So for the electric eel, so again, these are electrical plaques. These are special cells that have a voltage across them. Let's take a look at the very dangerous electric eel. All right, so. All right, so the electrical plaques in the South American eel are arranged in the 140 rows. We know this animal quite well, with each row stretching horizontally. And can along the body and containing 5,000 electroplaques. All right, so this is a nice parallel arrangement. So essentially, this can yield an EMF of 600 volts and a current of 1 ampere. Which is basically deadly. We're trying to mention when you get a shock of when you have a shock that is 1 ampere, you may not survive that. You know, you start having heart defibrillation, paralysis, heart paralysis right around 300 milliamperes. So you get shocked by electric eel, you will likely not live. All right, and 1 ampere is well beyond deadly for the human body, for the human being. All right, so again, this is electric eels are something you have to be very careful about. But the animals have a natural built-in electrical system. All right, and it's very similar to how we actually compose things, right? How we humans would make some sort of electrical system. All right, let's do some problems from OpenStax. OpenStax 21.14. All right. Standard automobile batteries have 6 lead acid cells. In series. creating a total EMF of 12.0 volts. What is the EMF of an individual lead acid cell? All right, well, the individual EMFs just add up, right? So they're in series. So in series, they add up. So 6 of these epsilons, and these are, again, these are lead acid cells. Each of them you can think of them as a power supply, are in series. They just add up, just like I showed earlier, and that's going to equal 12 volts. So simple algebra means you divide both sides by 6. Each one is going to be 2.0 volts. Okay, 21.16. Open stacks next. That one says, what is the output voltage of a 3.0000 volt lithium cell? In a digital wristwatch. That draws 0.300 milliampere. If the cell's resistance is 2.00 ohms. Okay, so what is the output voltage of a 3.0000 volt lithium cell in a digital wristwatch that draws 0.300 milliamperes if the cell's resistance is 2.00 ohm? All right, and so again, you know, the actual voltage is rated at 3.000 volts, but you're not going to get that terminal voltage because of internal resistance and current. And so let's let me erase this. I'll write down the givens here to remind us what we're talking about here. So essentially the EMF, the actual rated EMF across this wristwatch would be 3.0000 volts. Now it draws, it's going to draw a current of 0.300 times 10 to the negative 3 amperes. All right. And we're told that the resistance, the internal resistance of this wristwatch would be 2.00 ohms. So with that said, what is it? What is the output voltage, otherwise known as the terminal voltage, the output voltage? What's the voltage that's actually going to run the wristwatch? So that's going to be V is epsilon minus IR. B is going to be the 3.0000 volts minus the current 0.300 10 negative 3 amperes times 2.00 ohm. The actual output voltage, if I work this out, will be 2.9994 volts. That's the actual voltage that'll run the wristwatch. All right, got another problem. OpenStack's 21.17. All right, what's that say? A. What is the terminal voltage? It's a terminal voltage of a large 1.54 volt carbon zinc dry cell. Used in a physics lab. to supply 2.00 amperes to a circuit. If the cell's internal resistance is 0.100 ohms. And then B, how much electrical power does the cell produce? C, what power goes to the load? All right, so what is the terminal voltage of a large 1.54 volt carbon zinc dry cell used in a physics lab to supply 2.00 amperes to a circuit if the cell's resistance, internal resistance, sorry, is 0.100 ohms? B, how much electrical power does the cell produce? And C, what power goes to the load? So we have to kind of look at this very carefully, to really understand what is asking. All right. So I'll kind of mention that as I go along. I'm going to have to erase the board here. So again, keep these numbers in mind. Okay, so let me erase what I wrote. Let's work the problem out. All right, part A. What do we know? All right, so again, what is the terminal voltage of a large 1.54 volt carbon zinc dry cell? Stop right there. That means that the battery is actually being rated with an EMF of 1.54 volts. That would be epsilon. Continue reading. Used in a physics lab to supply 2.00 amperes to a circuit. Okay, I is 2.00 amperes. That's the current that's going to go through that power supply or that battery. If the cell's internal resistance is 0.100 ohms, little r is 0.100 ohms. That's the internal resistance of this battery. All right, that's what I know. And I want to find out what the terminal voltage is. So how do I figure that out? Well, again, the voltage is actually being delivered to out of the battery, which actually is going to be the potential difference across the actual battery terminals, will be the rated EMF of the battery, but minus IR. I being that is the current that's going through the battery, and R is the internal resistance. This is the actual voltage across the terminals. All right. So terminal voltage will be the 1.54 volts that the battery is rated for, minus, we're going to draw 2 amperes, 2.00 amperes, and the internal resistance is 0.100 ohms. That means the actual terminal voltage that will actually be across the battery is 1.34 volts. That's what I'm actually going to get out of the battery. Not 1.54 volts, but 1.34 volts. Okay. Part B says, how much electrical power does this cell produce? Okay, that means that's the actual electrical power produced by the cell itself. Okay, the actual cell, well, that would be what? P is I epsilon. The cell is actually producing epsilon, the actual dry cell itself. All right, so that power that cell produces, even though it's going to get yucked up by the internal resistance, that power that the cell actually produces itself inside of this battery will be the 2.00 amperes times epsilon, which is 1.54 volts. So that power will be 3.08 watts. So inside of the actual battery is rated as a power. Now it's because of its internal resistance, you get less out, but the actual battery, the actual dry cell itself, is actually going to give you that current multiplied by that actual battery voltage, the actual rating of the cell itself. Now, the last part saying, okay, what power goes to the load? What actual power goes to the load? Because so now we have this I epsilon, but now because of this current, there's going to be an I squared R depletion of power in the cell itself. All right, so the power that goes to the load, call it load, will be the I epsilon. But again, the battery itself is going to have depletion of power. We call it the famous I squared R heat. All right, so what actually goes to the load will be the I epsilon that I calculated right there, that 3.08 volt, no need to watts, I'm sorry, no need to recalculate that, minus the 2.00 amperes squared times the 0.100 ohms. So the actual power that goes to the load will be, when you calculate this, it'll actually be 2.68 watts. So again, that is the power generated by the actual dry cell itself minus the I squared R. Remember, this dry cell has its own internal resistance. So it's going to also operate as a resistor to some extent and give off I squared R heating. So it's going to be the I epsilon from the actual power delivered by the actual dry cell minus the I squared R heating, and 2.00 amperes squared times the internal resistance. All right, let's do another problem. I'm going to do OpenStax 21.23. Okay, that one says an automobile starter has an equivalent resistance of 0.0500 ohms and is supplied by a 12.0 volt battery. With a 0.0100 ohm internal resistance. Internal resistance. A, what is the current in the motor? B, what voltage is applied to it? C, what power is supplied to the motor? D, repeat these calculations when the battery connections are corroded. And add 0.0900 ohms to the circuit. All right. And it says in parenthetical sentence, significant problems are caused by even small amounts of unwanted resistance in low voltage, low current application. Sorry. So again, an automobile starter has an equivalent resistance of 0.0500 ohms. Again, you want to have a low resistance for a starter motor. All right. So again, the idea is you want to have the current going through as unimpeded as possible. And is supplied by a 12.0 volt battery with a 0.0100 ohm internal resistance. B, what is the current in the motor? B, what is the voltage? What voltage is applied to it? see what power is supplied to the motor. And D, now D, we're going to corrode the battery. So we're going to repeat these in calculations when the battery connections are corroded and add 0.0900 ohms to the circuit. We're having a bad battery, a worn out battery, a corroded battery, and so we're going to end up adding internal resistance to the battery. All right, so that's what this is about. So I'm going to try to do a side-by-side comparison as much as I can on working out this problem. So none of the calculations are too big. So again, for a real estate person, I need to erase all this stuff. Let's remind ourselves. I'll kind of remind you as I go along what the actual numbers are that we need. So for part A, what are we being asked again? Part A says, okay, what is the current in the motor? All right, so let's kind of write down what we know. The total resistance of this whole system, of the battery, is 0.0500 ohm. All right, and we know that the actual EMF, the rating of the battery itself, is going to be 12.0 volts. That would be the EMF of the battery. We also know the internal resistance, R, little r, has an internal resistance of the actual battery is 0.0100 ohm. All right, so the first thing we want to know is what is the current? So again, we're gonna want to use Ohm's law. I mean, effectively, what does this system look like? You kind of draw a little picture. Well, you have the battery itself, but it's going to have a little internal resistance R in it. Here's epsilon. But then the load itself would be given by the big resistance. You have a fairly simple circuit and you have a current going across it. That where your two resistors, the main resistor and the internal resistor, would be in parallel. Ohm's law would tell you, so using Ohm's law, we can write that essentially epsilon is I times the series equivalent of R, which would be little r plus big R. All right, and so you want the current, you would just solve for it, and that's epsilon divided by little r plus big R. Or the current in this case would be the 12 volt battery, 12.0 volts, and then divided by 0.0100 ohms plus big R, which is 0.0500 ohms. So your current in this particular case would be 200 amperes, very large. All right, so I'm going to kind of collect information here. So we're going to say good battery. Then I'm going to have another set of information that's going to be for the corroded battery. Okay, so again, remember this calculation. And so for the good battery, we have a current going through of 200 amperes. All right. Now, the next part says what voltage is applied to it. Okay, so now we know the current. Now the question is, well, what is the actual terminal voltage? All right, so we need to calculate the terminal voltage. We know what the true rated EMF is of the battery. What is the actual voltage that's being applied by the battery? Well, that would be what? V is epsilon minus IR. Again, the battery gets depleted. I mean, the battery, its actual effective terminal voltage reduces by the current running through it multiplied by the internal resistance, as we've seen. So the actual terminal voltage would then be the 12 volts minus the current I just got computing, 200 amperes, times the internal resistance of 0.0100 ohms. Again, using the internal resistance. When I compute that, I find out that the actual I'm not getting 10, 12 volts delivered to my system. I'm actually getting 10 volts delivered to my system. Why? Because I have the minus IR term that's pulling off of the actual rated EMF of the battery. So the terminal voltage I get is going to be 10 volts. I'm collecting my little my data here. And then finally, I want to find out what is the actual, let's see, what's the verbiage here? C says, what is the power supplied to the motor? When you're supplying power to the motor, unlike the previous question, I'm asking, what is the power supplied by the actual dry cell itself? Now we're asking, what is the power supplied to the motor? The motor sees not epsilon, the motor sees V. You know, basically the battery has two terminals connected to it. The terminal voltage is what actually goes to the motor, to the load. It's going to see epsilon minus IR. This is what's shown to the world. This is when you connect the battery by a couple of terminals, you're connecting to the terminal voltage V, even though the actual rated EMF of the battery is epsilon, right? So what would you do then? Well, you calculate the power as IV. The power delivered to the motor would be the current times the terminal voltage. That's what the motor sees, all right? Not epsilon. So you have 200 amperes multiplied by 10.0 volts. So what you get then is you're going to get 2,000 watts. Great. That's when I have a good battery. All right. Now we're going to corrode the battery. So for part B, we corrode the battery. We're essentially going to do what? We're going to increase R. So in part B, R is no longer 0.0100. Now I have a corroded battery, right? So R has increased. It's no longer 0.0100 ohms, but now because I have corrosion, I have to add 0.0900 ohms to it. So now the internal resistance of the battery, because it's become bad, is 0.1000 ohms. All right, so now let's redo these calculations. All right, and so again, as I said, I applied Ohm's law. So let's do bad battery. All right, so I want I want V, and I want P. And I'm going to compare them. You're going to see that having a bad battery really affects things. All right, so I'm going to go back to Ohm's law like before. Again, imagine I'm going to redraw that circuit that I did before. What would I get? I'd get that I is epsilon over little r plus big R. And now my little r is a lot worse. So I have the same 12-volt battery divided by 0.1000 ohms plus my internal resistance is actually bigger than my actual load resistance. 0.0500 ohms. When I do that calculation, I find out that unfortunately, what used to be 200 amperes worth of current has now been reduced to just 80 amperes. Now I only have 80 amperes of current, so things aren't going so well for my car. How about the other calculations? Well, now I want to figure out how much. So now I know that the current has greatly reduced. I want to find out part B. Part B is again what voltage is applied to it. Again, the voltage applied to the current is going to be the voltage that is. So it's going to be the terminal voltage. So we go back to our calculation for terminal voltage. We find out that terminal voltage is again what? It's the actual rated EMF minus IR. Well, now I have a corroded battery, so I have now 12 volts minus, now I only have 80 amperes going through it, multiplied by a much bigger 0.1000 ohms. I find out now that the terminal voltage that's going to be supplied by my battery to the motor will become 4 volts, 4.0 volts. All right, it used to be 10 volts. Now it's been reduced down to only 4 volts because I have a bad battery. How much power is now supplied to my motor? Well, at this point, P, again, is IV. I use V because V is what the motor sees, the terminal voltage. P is going to be this 80 amperes times just 4.0 volts. Well, that's not much. That's going to be 320 watts. So in my calculation, I have a nice fresh battery with a small internal resistance. The current given to the motor is 200 amperes. The voltage that essentially is supplied to the motor is 10 volts, and the power supplied to the motor is 2,000 watts. If I have a bad battery because it's corroded and the internal resistance goes up, now my current, instead of being 200 amperes, is now 80 amperes. My voltage supplied to the motor, instead of being 10 volts, is now 4 volts. I have a dead battery, basically. And the power supplied is 2,000 watts. That goes down to 320 watts. So the performance of my battery and how it operates the motor has been greatly reduced because of corrosion in the battery.